The studio lights dim to a soft amber glow, and beyond the anchor's desk stretches an infinite backdrop of stars. Not the harsh twinkling points you see on a cold winter night, but something gentler, more like the sky appears when you're halfway to sleep and your eyes are just barely open. The anchor settles into their chair with the quiet deliberation of someone who has all the time in the world, adjusts a single sheet of paper that doesn't really need adjusting, and looks directly into the camera with the kind of calm that makes your shoulders drop without you realizing it. Tonight's top story is not a crisis. It is not a storm bearing down on anyone's coast, not a disaster unfolding in real time, not something that requires you to check your phone or wake your neighbour, or do anything at all except perhaps pull your blanket a little higher and let the information settle over you like snow. Tonight's story is about a visitor, a traveller from somewhere else, passing through our corner of the galaxy so quietly that if you weren't paying attention, if you weren't one of the astronomers scanning the sky each night, or one of the spacecraft drifting through the solar system with their patient cameras, you might never know it was there at all. The visitor has a name, though it's the kind of name that sounds more like a catalogue number than something you'd call a guest. 3I Atlas. The 3I tells you it's the third interstellar object we've ever confirmed, the third thing we've seen that definitely, unmistakably came from another star system and is just passing through ours on its way to somewhere else, or nowhere in particular, which is more likely. The Atlas part tells you which telescope spotted it first, back on July 1st, 2020, when the Atlas survey in Chile was doing what it does every clear night, methodically photographing the sky, comparing each night's images to the night before, looking for anything that moved, and 3I Atlas moved. Not quickly, not dramatically, but with the steady, purposeful motion of something on a long journey. Right now, as you're hearing this, is making its way outward through the inner solar system, having already swept past the Sun and Venus and Mars, now crossing through the asteroid belt on a trajectory that will bring it closest to Earth on December 19th, 2025. But closest is a relative term when you're talking about space. On December 19th, this comet, because that's what it appears to be, a comet, a ball of ice and rock wrapped in a cloud of gas and dust, will still be about 1.8 astronomical units away from us. That's roughly 170 million miles, about 270 million kilometres, almost twice the distance between Earth and the Sun. You could fit another entire Earth-Sun system in the gap between us and this visitor, with room to spare. So there's no danger, no threat, no reason to look up at the sky with anything other than curiosity or wonder, or, honestly, complete indifference if you prefer. The comet poses no risk to our planet, won't change the tides, won't affect the weather, won't do anything except be there, very far away, visible only to telescopes moving through the dark. The anchor pauses, takes a slow breath, and continues in that same unhurried cadence, the kind of voice you might hear on a nature documentary about deep-sea creatures or the formation of mountains, phenomena that unfold on timescales so vast they make human urgency seem faintly absurd. This is a story about time and distance and the remarkable fact that, very occasionally, something from another star system wanders close enough for us to see. Let's talk about who this visitor is, or what it is, since calling a comet "who" might be giving it more personality than it actually has, though after you learn a bit about its journey you might feel differently. 3I Atlas has a more official designation too, C2025N1 Atlas, the kind of label that tells other astronomers exactly when and how it was discovered. The C means it's a comet, as opposed to an asteroid. The 2025 N1 tells you it was the first such object discovered in the first half of July 2025. Astronomers divide each year into half-month periods and assign letters to them, and N corresponds to early July. The Atlas, in parentheses, credits the survey that found it, but it's that 3I prefix that makes this comet special, that elevates it from just another icy visitor from the outer reaches of our solar system to something genuinely rare. The I stands for interstellar, and the number tells you this is only the third time we've confirmed such an object passing through our neighbourhood. The first was Oumuamua, discovered in 2017, that strange, elongated thing that tumbled through the inner solar system and sparked all kinds of speculation because it didn't look like anything we'd seen before. Not quite an asteroid, not quite a comet, accelerating in ways that were hard to explain with conventional physics alone. The second was 2I Borisov, found in 2019, which looked much more like a typical comet, and therefore reassured everyone that the universe wasn't necessarily full of Oumuamua-style oddities. And now we have 3E Atlas, which appears, at least so far, to be a very active, very comet-like object that just happens to be passing through from somewhere else. The anchor explains this gently, emphasizing that interstellar doesn't mean alien in the science fiction sense. No one is suggesting this is a spacecraft or a probe, or anything deliberately sent by another civilization. It means this comet formed around another star in another planetary system and was somehow ejected from that system millions or billions of years ago, sent wandering through the galaxy until gravity happened to steer it through our solar system now, in December 2025, while we're all going about our lives. How do astronomers know it's interstellar? How can they be so sure this isn't just a regular comet from the outer edge of our own solar system, maybe from the Oort cloud, that vast sphere of icy objects surrounding the Sun at immense distances? The answer lies in the comet's orbit, specifically in a number called eccentricity. Every orbit has an eccentricity value. A perfect circle has an eccentricity of 0. An ellipse, the shape of most planetary orbits, has an eccentricity between 0 and 1. And a parabola, the minimum energy path for something escaping a gravitational field, has an eccentricity of exactly 1. Anything with an eccentricity greater than 1 is following a hyperbola, which means it's moving too fast to be captured by the Sun's gravity. It's not bound to our solar system, it's just passing through, and once it leaves, it won't be back. 3 Atlas has an eccentricity greater than 1, significantly greater. The exact value depends on the precision of the measurements, but there's no ambiguity. This is a hyperbolic orbit. The comet is moving too fast and on a trajectory too steep to have originated from anywhere within the Sun's gravitational domain. It didn't get kicked out of the Oort cloud by a passing star. It didn't receive some gravitational assist from Jupiter that flung it onto this path. It came in already fast, already unbound from somewhere else. When astronomers trace its trajectory backward, projecting where it came from before the Sun's gravity bent its path, they find that it points toward the direction of the constellation Sagittarius, toward the dense star fields at the centre of our Milky Way galaxy. That doesn't mean it came directly from the galactic centre. Space is vast, and the comet could have been wandering for eons, gradually changing direction as it passed through the galaxy's gravitational field. But it definitely didn't come from the plane of our solar system, the flat disk where the planets orbit. It came in from a different angle, a different origin, carrying ice and dust that formed in the disk around another star. The anchor compares 3I Atlas to its 2 predecessors, not in a way that ranks them or judges, which is more interesting, but in a way that helps you understand what makes each one special. Oumuamua was the strange one, the outlier, the object that made everyone reconsider what interstellar visitors might look like. It was elongated, maybe cigar-shaped or pancake-shaped, depending on which model you believed. It had a reddish colour that suggested a surface baked by cosmic rays over millions of years. And it accelerated as it left the inner solar system, pushed by some force that wasn't quite explained by outgassing alone, though most scientists think that's still the most likely answer. Perhaps the way the gas vented from its surface created an asymmetric thrust, like a very slow, very uncontrolled rocket. Then came 2I Borisov, which looked much more familiar. It was clearly a comet, with a bright coma and a long tail, behaving just like comets from our own solar system behave when they get close to the Sun. Observations showed it had a composition similar to comets we know, perhaps slightly richer in carbon monoxide, but nothing wildly exotic. Borisov was reassuring. It suggested that most interstellar objects might be ordinary comets and asteroids, just from other neighbourhoods, and that Oumuamua's weirdness might have been an exception rather than the rule. 3 Atlas seems to fall somewhere in between, or perhaps it carves out its own category. It's clearly a comet, very active, very bright, releasing lots of gas and dust. But as observations accumulate, astronomers are noticing some unusual chemical signatures, some differences in composition that hint at formation conditions unlike those in our solar system. It's not so strange as to be inexplicable, but it's not so familiar as to be boring either. It's just different enough to be scientifically valuable, just similar enough to be understandable. The scene shifts now, though there's no jarring transition, just a smooth fade to an animation that shows the inner solar system from above, like you're looking down on the Sun and the planets from some vast height. The animation is slow, almost meditative, with orbits traced as pale lines and the sun a soft yellow glow at the centre. Into this calm diagram comes 3I Atlas, its path a sharp hyperbola cutting through the orderly circles and ellipses of the planets. The narrator walks through the comet's journey with the patience of someone describing the route of a train through a countryside you've never visited, but somehow makes you want to see. 3I Atlas, approached from the southern sky, coming in on a trajectory that's retrograde, meaning it's moving in the opposite direction to the planet's orbits, but nearly in the same plane. Most comets from the Oort cloud come in at random angles, plunging through the solar system from above or below the plane of the planets. This one, though, is tilted only about 5 degrees from the ecliptic, the plane where Earth and the other planets orbit. It's an unusual geometry, one that sparked extra curiosity among astronomers. Why would an interstellar comet happen to arrive on a path so closely aligned with our solar system's architecture? It's likely just a coincidence. Space is full of coincidences, but it's a neat one. The comet's path brought it first past Mars, which it approached on October 3rd, 2025, passing within about 0.19 astronomical units of the red planet. That's roughly 18 million miles, close enough that instruments on Mars orbiters might have caught a glimpse if they were pointed the right way, though Mars doesn't have the kind of observatories Earth does. Then 3 Atlas continued inward, reaching its closest point to the Sun, perihelion, on October 29th, 2025. Perihelion is the moment when a comet gets the hottest, when solar radiation beats down most intensely on its surface, vaporizing ice and sending plumes of gas and dust streaming outward. For 3 Atlas, perihelion was at about 0.63 astronomical units, well inside the orbit of Venus, closer to the Sun than Venus ever gets. The comet would have been baking, glowing, shedding material at its maximum rate. After perihelion, it swung past Venus in early November, then began its long climb back outward, crossing Earth's orbit, not Earth itself, but the path Earth follows around the Sun, and heading toward the asteroid belt. On December 19th, it will pass closest to Earth, though as we've established, closest still means 170 million miles away, a distance so vast that even if you had the world's best backyard telescope, you'd see only a faint smudge, if you could find it at all. Then the comet will continue outward, crossing the asteroid belt, passing through the orbit of Mars again, and heading toward another close encounter, this time with Jupiter, in March 2026. That Jupiter flyby will be the comet's last major gravitational interaction with anything in our solar system. Jupiter, with its immense mass, will tug on 3I Atlas as it passes, altering the comet's trajectory slightly, giving it a small gravitational kick. But even Jupiter's gravity won't be enough to capture this visitor. The comet is moving too fast, its hyperbolic trajectory too steep. After Jupiter, 3I Atlas will sail out past Saturn, past Uranus and Neptune, past the Kuiper belt and eventually past the Oort cloud, and then it will be back in interstellar space, alone again, wandering the galaxy for millions of years until perhaps, though the odds are vanishingly small, it passes through another star system and gives some other planets' astronomers something interesting to look at. The anchor emphasises, with the same calm assurance they've maintained throughout, that despite the dramatic language you might see in some headlines, words like mysterious object or approaching Earth, the distances involved here are enormous, the encounter utterly safe. For Earth, for us, this comet is simply passing through the neighbourhood, a quiet traveller visible only to those who know where and how to look. Now comes what you might think of as the roundup segment, where the programme checks in with various observatories and spacecraft that have turned their attention to 3 Atlas. It's framed almost like a series of remote correspondents reporting from different vantage points around the solar system, though of course there are no actual correspondents floating in space. There are only instruments, cameras, spectrometers, all operated by teams of scientists on Earth, but somehow the framing makes it feel like the solar system itself is watching, paying attention to this visitor. As soon as astronomers confirmed that 3I Atlas was indeed interstellar, NASA and the European Space Agency quickly organised a coordinated observation campaign. This is what happens when something genuinely rare appears. Resources get reallocated, telescope time gets rearranged, spacecraft schedules get adjusted. Everyone wants a look. Everyone wants data. Because who knows when the next interstellar object will come through? It could be next year. It could be 50 years from now. So when one appears, you observe it while you can. Ground-based telescopes in Hawaii, Chile, Australia. Sites chosen because they have clear skies, minimal light pollution, and are spread around the world so that at least one of them always has a view of the comet as Earth rotates, began tracking 3I Atlas shortly after its discovery. They measured its brightness, watching how it changed as the comet approached the sun and then receded. They analysed its spectrum, the rainbow of colours in its light, to identify what gases were boiling off its surface. They photographed its tail, tracking how it stretched and shifted as the solar wind pushed against it. These ground-based observations are the backbone of comet science, the steady accumulation of data night after night. But they can only see so much. Earth's atmosphere blurs fine details. Weather interrupts observations. Daylight makes half the sky inaccessible for half of every day. That's where space-based observatories come in, and that's where the story of 3I Atlas gets particularly interesting, because this comet happened to appear at a time when several spacecraft were positioned, more or less by chance, to get excellent views. The narrator likens this to a slow-moving parade, which is a gentle metaphor but also an apt one. Imagine a parade float drifting down a street so long you can't see either end, moving so slowly that each person along the route has plenty of time to watch it approach, pass directly in front of them, and then recede into the distance. 3I Atlas is the float. The observatories are the spectators. Each one gets a slightly different view, a different angle, a different moment in the comet's journey. First among these space-based correspondents is the Hubble Space Telescope, which has been orbiting Earth since 1990 and remains one of the most capable astronomical instruments ever built, despite being more than 3 decades old. Hubble has observed countless comets over the years, but an interstellar comet is special. On November 30th, 2025, Hubble turned its Wide-Field Camera 3 toward 3I Atlas and took a series of images, capturing the comet in exquisite detail. At the time of these observations, the comet was about 178 million miles from Earth, already near the distance it will have at closest approach on December 19th, just from a different angle. Hubble's images reveal several key features. There's the nucleus, the solid core of the comet. Though solid might be too strong a word, it's more like a loosely bound pile of ice and rock and dust, held together by its own weak gravity and by the stickiness of frozen volatiles. The nucleus is small, probably only a few hundred meters to a few kilometers across, too small for Hubble to resolve as anything other than a bright point. Surrounding the nucleus is the coma, a glowing cloud of gas, and dust that forms when solar heat vaporizes ice on the comet's surface. The coma is much larger than the nucleus, hundreds of thousands of miles across, and it has a teardrop shape, compressed on the side facing the sun by the pressure of solar radiation and the solar wind stretched out on the opposite side into the beginnings of a tail. Hubble's images show this structure clearly, the bright condensed heart of the coma where the nucleus sits, and the more diffuse outer regions where gas and dust gradually disperse into space. But the most interesting details are the faint plumes and jets visible in the images, subtle variations in brightness that hint at active venting from specific locations on the nucleus's surface. Comets aren't uniform. Their surfaces are patchy, with some areas covered in darker, more inert material, and other areas where fresh ice is exposed. As the nucleus rotates, most comet nuclei spin, tumbling through space with periods of hours or days. Different areas get exposed to sunlight, and jets of gas and dust shoot out from these active regions. Hubble's images show at least 2 or 3 distinct jets around 3I Atlas, suggesting that its nucleus has an irregular shape and a complex surface. These observations help astronomers estimate the comet's size more precisely. By measuring how much sunlight reflects off the coma and the nucleus, and by modelling how much gas and dust the comet is releasing, they can work backward to estimate the size of the solid core. Current estimates put it somewhere between a few hundred meters and a couple of kilometers across, which is small by comet standards, smaller than the nucleus of Halley's comet, for instance, but not unusually so. It's about the size of a mountain, give or take. The narrator emphasizes gently that these observations show 3 Atlas behaving like a typical active comet despite its exotic origin. It's not doing anything strange or inexplicable, it's just following the physics of ice and sunlight and gravity, the same physics that governs all comets. The fact that this one formed around another star makes it scientifically precious, but it doesn't make it alien in any unsettling sense. Next, the program hands off to another correspondent, this one much farther from Earth. The European Space Agency's Jupiter Icy Moons Explorer, known by the acronym JUICE, is currently on a long looping cruise through the inner solar system, using flybys of Earth and Venus to gradually build up the speed it needs to reach Jupiter in the early 2030s. Right now, JUICE is in a strange sort of limbo, coasting through space with most of its instruments powered down to conserve energy, its main science mission still years away. But when an interstellar comet appears, you turn on whatever instruments you can spare. On November 2nd, 2025, as 3i Atlas was climbing back outward from perihelion, JUICE was in a position to get a relatively close look. Close by the standards of interplanetary space, anyway. The spacecraft was about 41 million miles from the comet, a distance that sounds enormous but is actually quite near compared to ground-based observations. From that range, even JUICE's simple navigation camera, a low-resolution instrument designed mainly to help engineers on Earth figure out where the spacecraft is pointing, managed to capture a revealing image. The image is grainy, not the kind of thing you'd frame and hang on a wall, but it shows everything you need to see. There's the nucleus, a bright point-like source in the centre. Surrounding it is the glowing coma, a roughly circular halo of light. And stretching away from the nucleus, visible even in this simple snapshot, are two faint tails. A dust tail, made of microscopic particles that reflect sunlight, and a plasma tail, made of ionized gas that glows faintly as it's swept away by the solar wind. The tails are key. They're the most visually striking feature of a comet, the reason comets appear in ancient records and inspire awe. But they're also scientifically useful. The dust tail shows you the distribution of particle sizes and the rate at which material is being shed. The plasma tail shows you how the comet is interacting with the solar wind, how fast it's releasing gas, what molecules are present in that gas. From JUICE's vantage point, both tails are visible, confirming that 3i Atlas is a vigorous, active comet. The full scientific data from JUICE's instruments, higher resolution images, spectra, other measurements, will take longer to downlink back to Earth. The spacecraft's main antenna is powerful, but the data rate is slow when you're tens of millions of miles away, and JUICE has limited storage and limited windows when it can communicate with ground stations. Most of the detailed JUICE data from this flyby is expected to arrive in 2026, after it's been prioritised and queued and transmitted during scheduled communication passes. But the fact that the spacecraft managed to capture anything at all, with its simple navigation camera, during what is essentially its interplanetary commute, adds another piece to the puzzle. The tone here is patient, unhurried. There's no rush. The data will arrive when it arrives. Scientists will be analysing observations of 3i Atlas for years, comparing notes, refining models, writing papers. This is not a story with a resolution that comes next week or next month. It's a story that unfolds slowly, like the comet's own journey through the solar system. Now another observatory enters the picture, though this one doesn't take pictures at all. The XMM-Newton X-ray Observatory, operated by ESA and launched in 1999, is designed to detect X-rays from cosmic sources, supernova remnants, black holes, galaxy clusters, objects so hot or so violent that they emit light at the high-energy end of the spectrum. Comets don't normally emit X-rays. They're cold, icy objects, the opposite of hot, but they can glow faintly in X-rays due to a surprising mechanism that involves the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun at hundreds of miles per second. When this wind encounters the neutral gas in a comet's coma, something interesting happens. Highly ionized atoms in the solar wind, atoms that have been stripped of multiple electrons by the Sun's intense heat, collide with neutral molecules in the coma and steal electrons from them. This charge exchange releases energy in the form of X-rays, creating a faint halo of high-energy light around the comet. It's a subtle effect, and detecting it requires a sensitive X-ray telescope with a long exposure time. On December 3rd, 2021, XMM-Newton observed 3i Atlas for about 20 hours, staring at the comet with its X-ray cameras, accumulating photons. The goal was to measure the X-ray halo, to quantify how much gas the comet is releasing, and to probe the interaction between the solar wind and material that formed around another star. The narrator explains this in simple terms, comparing the X-ray glow to a very faint, high-pitched hiss that occurs where sunlight, solar wind, and alien ices meet. It's not something you could see with your eyes, not something that affects the comet's appearance in visible light, but it's a signature of the physical processes at work. Observing this halo can reveal details about the comet's composition, what kinds of molecules are present in the coma, how dense the gas is, how fast it's expanding outward. And because these X-ray observations are difficult and time-consuming, getting them for an interstellar comet is a rare opportunity. XMM-Newton's data will also take time to analyse fully. X-ray astronomy is a specialty, requiring careful calibration and modelling to separate the faint signal of the comet from the background noise of the X-ray sky. But preliminary reports suggest the observations were successful, that the X-ray halo was detected, and that 3I Atlas is behaving once again like a typical comet, releasing gas at rates consistent with its size and distance from the Sun. The story shifts now to a slightly different angle, something closer to colour commentary than straight reporting. Observers using the Gemini North Telescope in Hawaii, along with several other ground-based facilities, have been tracking 3I Atlas's brightness and colour as it moves away from the Sun. One of the most striking findings is that the comet has become noticeably greener since passing perihelion in October. Green comets are not unusual. Many comets take on a greenish hue as they approach the Sun. But the colour is distinctive and interesting. It comes from molecules like diatomic carbon, a simple molecule made of two carbon atoms bonded together, which fluoresces under solar ultraviolet light, emitting a characteristic green glow. Other molecules, including cyanogen and molecular carbon, can also contribute to the green colour. The fact that 3I Atlas is getting greener as it moves away from the Sun suggests that its nucleus is still warm enough to release these gases, that it's still actively venting material even as it climbs back outward through the inner solar system. But the green colour is just the most visually obvious part of a broader set of chemical observations. A NASA-led campaign involving multiple telescopes and spectrometers has been measuring the comet's spectrum in detail, identifying the specific molecules present in its coma. The findings are intriguing. 3I Atlas appears to have a higher ratio of carbon dioxide to water than most comets in our solar system. It also shows strong emissions of nickel and iron, metals that are present in all comets but seem to be particularly abundant in this one. These differences don't mean the comet is artificial or dangerous. The narrator is careful to stress this, knowing that any mention of unusual chemistry can spark speculation. What these differences suggest, instead, is that 3I Atlas formed in a planetary system with conditions slightly different from those in our own solar system. Maybe it formed farther from its star, where temperatures were colder and carbon dioxide ice was more stable. Maybe its parent system's protoplanetary disk had a different ratio of elements, slightly more carbon or slightly more metals, due to the particular mix of materials that went into forming that star. The point is that 3I Atlas is giving us a sample of another star system's raw materials, and those materials are not quite the same as ours. It's like tasting bread from a bakery in another country, and noticing that the flour tastes slightly different, the water has a different mineral content. The bread is still bread, the comet is still a comet. But the details matter, because they tell us about the variety of conditions under which planets and comets can form. In a very gentle transition, the programme now addresses something that some viewers might have heard about, might be curious about, might even be a bit concerned about. There has been some speculation, from certain quarters, about whether 3I Atlas might be something other than a natural comet. Specifically, Harvard astrophysicist Avi Loeb, who previously proposed that 1 Oumuamua might have been an artificial object, perhaps a light sail from another civilization, has pointed out some features of 3I Atlas's trajectory and activity that he finds intriguing. Loeb has noted the comet's unusual orbital alignment, the fact that it came in nearly along the plane of our solar system's planets. He's pointed out the jets visible in Hubble's images, suggesting they might not be entirely random. He's speculated, in the careful, hedged language of a scientist who knows he's pushing boundaries, that it might be worth considering, just considering, the remote possibility that this could be a probe, a buoy, something sent deliberately. The program treats this speculation with respect, but also with context. The narrator explains that most researchers strongly favour a natural explanation. 3 Atlas looks like a comet, behaves like a comet, has a composition consistent with comets. Its differences from solar system comets are interesting but not inexplicable. They simply reflect its origin in a different planetary system. The jets visible in Hubble's images are consistent with the kind of asymmetric outgassing that happens when a rotating, irregularly shaped nucleus exposes different patches of its surface to sunlight. The orbital alignment, while neat, is not so improbable as to demand an extraordinary explanation. Orbits are essentially random in 3 dimensions, and sometimes random orbits happen to align with interesting features by chance. The tone is calm, balanced, even generous. Science thrives on testing odd possibilities, on entertaining hypotheses that seem unlikely but can't be ruled out completely. Loeb's speculation is in that spirit. But current evidence comfortably fits an ordinary if exotic comet. The program doesn't mock the speculation, doesn't dismiss it harshly, but it also doesn't linger on it. It's one data point in a much larger story about what we're learning from this visitor. Now comes the big picture segment, the part of the program that steps back and asks why this flyby matters, why astronomers are devoting so much time and so many resources to watching what is, after all, just a small ball of ice and rock that will be gone in a few months and never return. The answer has to do with what 3I Atlas represents, a physical sample of another star's debris, a chunk of the raw materials that went into building planets around another sun. We can observe other planetary systems with telescopes. We can see the planets themselves, at least the large ones, as they pass in front of their stars or as their gravity tugs on their stars. We can analyse the light from those stars and infer what elements are present. But we can't reach out and touch anything. We can't bring a sample back to a laboratory. We can't measure the exact isotopic ratios of the ice or the precise abundances of trace metals in the dust. 3I Atlas gives us that. It's not a deliberately collected sample, not something we sent a spacecraft to retrieve, but in some ways it's even better because it's uncontaminated by human intervention. This is a piece of another planetary system that fell into our laps, and we have a few months to study it before it leaves forever. The composition of 3I Atlas can test theories about how comets form. Comets are thought to be leftovers from planet formation, bits of ice and rock that never got incorporated into planets and have been wandering the outer reaches of their star systems ever since. By comparing the composition of an interstellar comet to comets from our own solar system, astronomers can see which features are universal, presumably the result of fundamental physics and chemistry that apply everywhere, and which features are specific to particular systems, the result of local conditions like the star's temperature or the disk's initial composition. The activity level of 3I Atlas, how much gas and dust it's releasing, can tell us about the structure of its nucleus. Comets that formed in very cold conditions, far from their stars, might have preserved more of the primordial ices that were present in the protoplanetary disk. Comets that formed closer in might have lost some of their more volatile ices early on. By watching how 3I Atlas behaves as it heats up near the Sun, astronomers can infer what kinds of ices are present and how deeply they're buried. And then there's the broader statistical question. How common are interstellar objects? We've now seen 3 in less than a decade, which suggests they're passing through the solar system fairly regularly. But how regularly? Are we seeing 1 per year on average, or 1 per month, or 1 per week? The answer depends on how sensitive our surveys are, how much of the sky we're monitoring, how faint an object we can detect. As surveys like Atlas and others improve, we'll detect more interstellar objects, and the statistics will improve. Comparing the compositions and behaviours of multiple interstellar visitors will help us build a picture of what's typical and what's unusual among planetary systems across the galaxy. The narrator emphasises that these are slow, patient questions. Data from 3I Atlas will be analysed for years, fed into models, compared with data from future interstellar visitors. This is not a story with a quick resolution. It's a story that contributes to a longer, deeper understanding of how planets form, how common different types of planetary systems are, what the galaxy's inventory of small bodies looks like. The broadcast is winding down now, the lights in the studio dimming even further, the stars in the backdrop seeming to grow brighter, though that might just be a trick of perception as your eyes adjust. There's a montage, a series of slow, dreamy images that feel more like poetry than documentary. A backyard astronomer standing in a dark field, far from city lights, their telescope pointed upward at a patch of sky that looks to the untrained eye like any other patch of sky. Maybe they can see Three-Eye Atlas, a faint fuzz through the eyepiece, or maybe they can't. Maybe the comet is too faint, too far, too diffuse. But they're looking. They're paying attention. Then Hubble, drifting silently in its orbit above Earth, sunlight glinting off its solar panels, its cameras pointed out toward the darkness where the comet glides. No sound, of course. Space is silent. But you can almost imagine a hum, the whir of mechanisms, the patient clicking of data being recorded, stored, transmitted. Juice, coasting through the inner solar system, its golden body catching the sun's light, its instruments powered down except for the ones that were briefly awakened to glimpse this visitor. It's on a long journey to Jupiter, years still ahead, but this detour, this chance encounter with an interstellar comet, is a bonus, an unexpected gift. XMM-Newton, listening for X-rays in the dark, its mirrors collecting photons that have travelled from the comet's coma through the vastness of space to this telescope that orbits Earth every 2 days, sweeping across the sky in search of the high-energy universe. And finally Earth itself, turning slowly beneath a sky full of stars, continents and oceans rolling past in the light and the dark, billions of people going about their lives, most of them completely unaware that an interstellar visitor is passing by right now, this very moment, on its long, lonely journey from one star system to nowhere in particular. The host's voice returns one last time, calm and reassuring, the same voice that started this broadcast. On December 19th, they say, while most of us go about our lives, working, shopping, cooking dinner, putting children to bed, scrolling through our phones, worrying about the small concerns that fill a human day, 3 Atlas will glide past at a distance so vast that it might as well be in another world, and in a sense it is. It belongs to the space between stars, to the cold, dark stretches of the galaxy where light takes years to travel from one point to another, and where matter is spread so thin that you could sail for centuries without encountering anything at all. The comet will pass by harmlessly, leaving no mark on our planet except in the form of data, gigabytes of images, spectra, measurements, numbers in databases that astronomers will pore over for years, looking for patterns, testing theories, refining their understanding of how the universe works. It will leave a beautiful trace in our instruments, in our telescopes, in the careful observations of people who have devoted their lives to watching the sky. And then it will be gone. After the Jupiter flyby in March 2026, after the long climb outward through the outer solar system, past the orbits of Saturn and Uranus and Neptune, past the Kuiper belt where Pluto orbits, past the heliopause where the sun's influence finally fades and interstellar space begins, Three-Eye Atlas will leave our solar system behind. It will be alone again, a small chunk of ice and rock tumbling through the galaxy, carrying with it no memory of this brief encounter, no record of the telescopes that watched it, or the people who wondered about it. But we will remember. We'll have the data, the images, the measurements. We'll have the knowledge that for a few months in 2025, something from another star passed close enough for us to see, and we paid attention. We turned our instruments toward it. We asked questions. We learned what we could. The final image is simple. The Milky Way stretched across a dark sky. Thousands of stars visible. The faint band of light that is our galaxy seen, edge on from our position within it. Somewhere among those stars is the one where 3 Atlas formed, though we don't know which one, and probably never will. It could have been ejected billions of years ago when its parent star was young and its planetary system was still settling into its final configuration. Or it could have been thrown out more recently, in some gravitational reshuffling, some close encounter with a passing object that sent it spinning out into the dark. Either way, it's here now, passing through our neighbourhood, a quiet traveller on an infinite journey. The studio lights fade to black, the stars remain. And somewhere, 170 million miles away and getting farther every second, a small comet continues on its way, indifferent to our telescopes, our curiosity, our wonder. It's just ice and rock and dust, following the laws of gravity and momentum, moving through space the way all things move through space, steadily, patiently, without hurry or destination. The program ends with silence, or perhaps with very faint music, something ambient and spacious, chords that resolve slowly and leave you feeling not anxious or excited, but simply aware. Aware that the universe is vast, aware that even in our little corner of it, remarkable things pass by all the time if we know where to look. Aware that tonight, as you sleep, as the world turns beneath the stars, an alien comet is making its quiet flyby, watched by patient instruments, recorded by careful observers, witnessed by a species curious enough to notice when something from elsewhere passes through. And that's all. That's the story. A visitor from another star, here for a moment, then gone. The cosmos continues. The telescopes keep watching. We go about our lives carrying the knowledge that we're not alone in the galaxy, not because we've found other civilizations, but because we've found evidence of other planetary systems, other collections of ice and rock orbiting other suns, and occasionally one of those pieces breaks free and wanders through the dark until it happens to pass by us, giving us a glimpse of what exists out there in the vast distances between stars. Sleep well. The comet is harmless, far away, on its long journey to nowhere. And we are here, safe on our planet, spinning through space as we always have, part of something much larger than ourselves, witnessing what we can, learning what we can, grateful for every visitor that gives us a story to tell. The next story is about to begin. Please relax and enjoy. You settle in as the studio lights dim to their gentlest setting, the kind of soft amber glow that reminds you of candlelight but steadier, more forgiving on tired eyes. Behind the anchor's desk, a backdrop slowly shifts through shades of deep blue and violet, scattered with points of white light that could be distant stars or perhaps just pleasant illusions meant to calm rather than inform. The anchor herself sits with her hands folded on the desk, papers before her that she barely glances at, and when she speaks, her voice arrives like something carried on a night breeze, unhurried and warm. Tonight's main story, she tells you, is about a single star, and though that star died long ago, its final light has only just reached our telescopes after travelling for 13 billion years through the expanding darkness of space. She wants you to know right away that this is not a story about danger or crisis, not a warning or a countdown, but simply a quiet update from the frontier of what we can see, a small addition to humanity's long list of things we have learned by looking up. The star in question exploded when the universe was only 730 million years old, which is to say it died when everything was still new, still forming, still working out the basic rules of galaxies and elements and light. The James Webb Space Telescope, our newest eye on the cosmos, caught the fading glow of that explosion, and in doing so gave astronomers the earliest confirmed supernova ever observed, a record that pushes our vision of stellar death back more than 1 billion years deeper into time than ever before. The anchor pauses to let you absorb this, her expression neutral but kind, the way someone might look at you if they were telling you about a distant relative you never met, someone whose life was lived long before you were born but whose story still matters in some abstract genealogical way. She explains that in March of this year, high-energy observatories detected a brief intense burst of gamma rays flashing across the sky, a phenomenon that happens somewhere in the universe roughly once a day, but which astronomers have learned to treat as a signpost, a cosmic flare that marks the location of something dramatic and distant. This particular burst was catalogued as GRB 24V314A, a designation that sounds clinical but which represents a moment of violent transformation, the final throes of a massive star collapsing under its own weight and releasing more energy in a few seconds than our sun will emit over its entire 10 billion year lifetime. Telescopes on the ground and in space swung into action, following the standard protocol for gamma-ray burst follow-up. They watched the afterglow, that fading ember of light that lingers after the initial flash, and they measured its properties, trying to determine how far away the event occurred and what kind of object produced it. The measurements suggested something extraordinary, a distance so great that the light had been travelling toward us since the universe was still in its infancy. And so the team requested time on the James Webb Space Telescope, the only instrument with the sensitivity and resolution to confirm what they suspected. The program now shifts. The camera pulling back from the anchor's desk and transitioning to a slow, computer-generated visualization of the James Webb Space Telescope itself, that golden hexagonal mirror floating in the blackness beyond the moon's orbit, positioned at a gravitationally stable point called L2, where it can stare continuously into deep space without the glare of Earth or the sun interfering with its vision. The narrator's voice continues, explaining in that same unhurried cadence that Webb was designed to see the universe in infrared light, wavelengths longer than visible red, and that this capability makes it uniquely suited for studying the most distant galaxies. Because as space expands, it stretches the light from faraway objects, shifting even ultraviolet and visible light into the infrared by the time it reaches us. The telescope looks fragile in the animation, its sun shields spread like golden foil, its mirrors arranged in that distinctive flower-like pattern. But you're reminded that this delicate-looking machine is among the most sophisticated instruments humanity has ever built, capable of detecting the faint warmth of a bumblebee on the moon, or more relevantly, the dying light of a star from when the universe was barely 500 million years old. Supernovae were not Webb's primary mission, the narrator notes. The telescope was built to study the first galaxies, to peer through dust clouds where stars are born, to analyse the atmospheres of planets around other stars. But its extraordinary sensitivity means that when a gamma-ray burst goes off in the early universe and someone requests follow-up observations, Webb can spot details that no previous telescope could see, including the faint smudge of a tiny galaxy and the lingering glow of a single exploding star. The visualization fades and you're taken on a conceptual journey backward through time, not with frantic urgency, but with the slow, meditative pace of someone walking you through a museum of natural history, pointing out the layers of rock and fossil that mark different eras. The narrator invites you to imagine the universe as it is now, 13.8 billion years old, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, a cosmos so vast and mature that it can seem almost static, unchanging on human timescales. Now, she says, we will rewind, not all the way to the Big Bang itself, but to a point just 730 million years after that initial moment of creation, a time when the universe was only about 5% of its current age. This was an era that astronomers call the Epoch of Ryanization, a name that sounds technical but which describes something fundamental, the period when the first generations of stars and galaxies were turning on, gradually filling the universe with light and energy, breaking apart the neutral hydrogen atoms that pervaded space, and creating the transparent, ionized medium through which light can travel freely today. Before this epoch, the universe was dark, a fog of neutral gas that absorbed most wavelengths of light, and after it the universe was clear, lit from within by countless stars. The supernova that Webb observed happened right in the middle of this transition, a single massive star in a small galaxy that was among the very first structures to condense out of the primordial gas, and its death would have contributed in some tiny way to the clearing of that cosmic fog, releasing energy and heavy elements into its surroundings. The narrator emphasizes that catching a single star's death from this epoch is like hearing one clear note from the universe's first orchestra, a metaphor she lets hang in the air for a moment before moving on. The program now shows you a simple infographic, animated in soft colours against a dark background, explaining what a gamma-ray burst actually is for those who might not know. These are the brightest electromagnetic events in the universe, brief flashes of the highest energy light, lasting anywhere from a fraction of a second to several minutes, and they come in two main varieties. Short bursts, which are thought to result from the collision of two neutron stars or a neutron star and a black hole, and long bursts, which are associated with the collapse of very massive stars into black holes. GRB 2503.4a falls into the latter category, a long burst, and the infographic walks you through the process in gentle steps. Imagine a star at least 20 or 30 times the mass of the Sun, the narrator says, burning through its nuclear fuel at a furious rate, its core fusing hydrogen into helium, helium into carbon and oxygen, and so on up the periodic table, until it has built an iron core that can no longer sustain fusion. At that point, the core collapses catastrophically, falling inward in less than a second, and if the star is massive enough and rotating rapidly enough, the collapse can punch through to form a black hole, while simultaneously launching twin jets of material outward at nearly the speed of light. if one of those jets happens to be pointed toward Earth, we see a gamma ray burst, a searchlight beam of high-energy photons that can outshine entire galaxies for a few seconds before fading away. The infographic fades and you return to the anchor, who explains that gamma ray bursts are used by astronomers as cosmic signposts precisely because they are so bright and so brief. When a burst is detected, telescopes around the world and in space immediately begin observing the same patch of sky, watching for the afterglow, which is a broader wavelength emission that lingers for hours, days, or weeks as the jet ploughs into the surrounding gas and heats it. By studying the spectrum of this afterglow, astronomers can measure how much the light has been redshifted by the expansion of the universe, and from that redshift they can calculate the distance to the source. In the case of GRB 25314a, early observations suggested a very high redshift, meaning a very great distance, and this triggered the request for Webb's involvement. The anchor describes this process not as a race or a competition, but as a careful, collaborative effort, with different teams contributing different pieces of the puzzle. The gamma-ray observatories that first spotted the burst, the ground-based optical and infrared telescopes that track the afterglow, and finally Webb, which provided the sharpest, deepest view of the host galaxy and the fading supernova. The next segment feels like a field report from deep space, though of course there is no reporter actually out there, only the data streaming back from Webb's instruments. The narration walks you through what happened after the gamma-ray burst in March. Ground-based telescopes and space-based observatories watched the afterglow over the following days, and their measurements of the spectrum revealed absorption lines from hydrogen and other elements that had been shifted far into the infrared, a clear sign that the source was extremely distant. The Webb team scheduled observations quickly, within weeks of the burst, using the telescope's near-infrared camera and its spectroscopic instruments to zoom in on the faint patch of sky where the burst had occurred. What Webb saw was a tiny host galaxy, not a grand spiral or a massive elliptical, but a small irregular cluster of stars, likely containing only a few million solar masses of material, a mere suggestion of a galaxy by modern standards. Within that galaxy, at the exact position where the gamma-ray burst had been detected, there was a point of light, faint and reddish, that matched the expected signature of a supernova's afterglow. By measuring the precise redshift of this galaxy, Webb's instruments confirmed what the earlier estimates had suggested. The light had left this star when the universe was only about 730 million years old, making this the oldest supernova ever directly observed, beating Webb's own previous record from a supernova seen at a time when the universe was about 1.8 billion years old. The narrator takes a moment to explain how astronomers confirmed that this was indeed a supernova and not some other kind of transient event, because in astronomy it is not enough to see something bright and fading. You must also understand what you are seeing. Webb's images taken months after the initial gamma-ray burst still showed a lingering glow at the same spot, and the way this glow faded over time matched the theoretical models of a supernova, not the simpler, faster decline of a gamma-ray burst afterglow alone. Spectroscopic observations revealed the chemical signatures of heavy elements, the kind of elements that are forged in the nuclear furnace of a supernova explosion. Oxygen, magnesium, silicon, iron. These elements were not present in the universe immediately after the Big Bang. Hydrogen and helium and a trace of lithium were the only elements created in the first minutes of cosmic time. Everything heavier, everything that makes up planets and people and the chemistry of life, was made later, inside stars, and released into space when those stars died. The supernova that Webb observed was one of the very first such events, one of the earliest contributions to the cosmic inventory of heavy elements, and the fact that Webb could see it, could measure its properties, could confirm its nature, is a testament to how far our observational capabilities have come. A researcher is paraphrased as saying that only Webb currently has the sensitivity and resolution to directly show that a gamma-ray burst from such a distant galaxy came from a supernova, and you are meant to understand this not as boastfulness, but as a simple statement of fact, a recognition that this discovery was only possible because we built a telescope specifically designed to see faint, distant things in infrared light. The program now shifts to what you might call the science desk, though there is no desk, only a calm voice and simple visuals that help you understand why astronomers are excited about this discovery. The excitement, the narrator explains, comes from what this supernova can tell us about the first generations of stars, those early suns that formed from the pristine hydrogen and helium gas left over from the Big Bang. These stars, often called population 3 stars, are thought to have been different from the stars we see in the universe today, likely more massive on average, burning hotter and faster, living for only a few million years before exploding, compared to the billions of years that a star like our Sun can sustain itself. Because they contained no heavy elements to start with, their nuclear physics and their structure would have been different, and their supernovae would have been the first events to enrich the universe with carbon, oxygen, and all the other elements that later stars would incorporate. The narrator is careful to note that the star associated with GRB 250314a was not necessarily a true population 3 star. Its galaxy may have already had a few cycles of star formation, enough to contaminate the gas with trace amounts of heavy elements. But even so, it was a very early star, a representative of the first few generations, and its death gives us a data point, a quiet clue about how quickly heavy elements appeared in small newborn galaxies and how fast they began to enrich the surrounding intergalactic medium. The visuals show a simple animation of a small galaxy, just a cluster of bright points representing stars, and one of those points suddenly brightens and then fades, leaving behind an expanding shell of colour that represents the elements ejected by the supernova. The narrator explains that each such explosion seeds its environment with the building blocks of future complexity, and that over hundreds of millions of years, countless supernovae from countless small galaxies gradually turn the universe from a place of simple, pristine gas into a place where chemistry could happen, where molecules could form, where eventually planets and life could arise. This is not presented as a grand emotional narrative, but as a matter of fact, a slow process playing out over cosmic time, and the discovery of GRB 250314a is simply one more piece of evidence, one more measurement to add to the growing data set of early universe supernovae. The narrator reminds you that science often progresses not through sudden revelations, but through the accumulation of many small observations, each one refining our models, each one narrowing the range of possibilities, and this discovery is part of that patient incremental process. There is a brief recap now, a summary of what has been learned, delivered in the same calm tone that has characterized the entire broadcast. The James Webb Space Telescope has confirmed the earliest known supernova, an explosion that occurred 730 million years after the Big Bang, initially detected as a gamma-ray burst in March of this year, and later confirmed through Webb's infrared imaging and spectroscopy. This discovery breaks Webb's own previous record for the most distant supernova by more than 1 billion years of cosmic time, pushing our direct observations of stellar death back into the epoch of reionization, a critical period in the universe's history. The narrator notes that this is unlikely to remain the record for long. Astronomers expect more such discoveries as they systematically search for gamma-ray bursts and follow them up with Webb and other telescopes. The goal, she explains, is not to keep breaking records for their own sake, but to build a catalogue of early supernova, to understand how common they were, how they varied in their properties, how they contributed to reionization and to the chemical evolution of galaxies. This is framed not as a race, but as a survey, a long-term project that will unfold over years and decades, with each new discovery adding to our understanding in small increments. The narrator mentions future plans without urgency or hype. There are other gamma-ray bursts that have been detected and are awaiting follow-up observations, and there are proposals to use Webb and other telescopes to search systematically for transient events in the early universe. The upcoming extremely large telescope, currently under construction in Chile, will have even greater light-gathering power than Webb, though it will observe invisible and infrared wavelengths from the ground rather than from space. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will have a much wider field of view than Webb, allowing it to survey large areas of sky and potentially catch more of these rare distant events. But all of this is described in a matter-of-fact way, as a continuation of the work that is already underway, not as a dramatic new chapter. The message is that science proceeds, telescopes improve, our catalogue of knowledge expands, and each generation of instruments opens new windows even as it answers old questions. The broadcast now begins its closing sequence, and the tone shifts subtly, becoming even more reflective, more suited to the late hour and the intended purpose of this programme, which is not to inform in the sense of delivering urgent news, but to soothe, to provide a gentle narrative that can accompany you as you drift towards sleep. The visuals show Earth from space, the globe slowly rotating, city lights glimmering on the night side like scattered jewels, and above it the stars, countless points of light that have been watching over this planet long before there were cities or lights, or anyone to look up at them. The narrator's voice invites you to imagine the James Webb Space Telescope out there beyond the moon, beyond the orbit of communication satellites and weather satellites, and all the busy infrastructure of near-Earth space, sitting in its quiet gravitational pocket, its sunshield always oriented to block the light and heat of the sun and earth and moon, its mirrors always facing the other direction, out into the deep. It collects photons one by one, the narrator says, particles of light that have been travelling through space for billions of years, some of them arriving from galaxies that formed when the universe was young, some of them carrying the last light from stars that died before our solar system even existed. You're reminded that while you sleep tonight, the telescopes continue their patient work. Webb does not rest. It observes target after target, its schedule filled months in advance, with requests from astronomers around the world, each one hoping to glimpse some distant or faint or fleeting phenomenon. Ground-based observatories scan the skies for transient events, their automated systems flacking anything that appears or changes or moves, feeding data to researchers who will analyse it in the morning. The universe is not waiting for us to catch up. It continues to make and lose stars, to form and destroy galaxies, to expand and cool and evolve according to physical laws that were set in motion billions of years ago. But the pace of these changes is so slow on human timescales that the sky above your window tonight looks exactly the same as it did last night, and will look the same tomorrow night. A comforting constancy that has guided travellers and inspired poets and provided a sense of scale and wonder for as long as humans have been able to look up. The narrator brings you back to the story of GRB 250314, A One Last Time, but now it is framed not as a scientific achievement or a record-breaking discovery, but as a single note in a vast, ongoing symphony. Somewhere in a small galaxy that no longer exists in the form it had 13 billion years ago, a massive star exhausted its fuel and collapsed, sending out a beam of gamma rays that travelled across the expanding universe, across billions of light-years of space, until finally, in March of this year, those gamma rays arrived at Earth and triggered detectors in orbit. The light from the subsequent supernova followed, stretched into the infrared by the expansion of space, faint but detectable, and Webb caught it, measured it, confirmed it. That star has been gone for 13 billion years, and the galaxy it lived in has likely merged with others, grown larger, changed shape, evolved into something we might not recognise. The supernova's ejecta, the elements it released, have long since mixed into the interstellar medium, been incorporated into new stars, perhaps even into planets, perhaps even into living things if any have arisen in that distant corner of the universe. We will never know the full story of that star or that galaxy, but we have this one snapshot, this one moment of death captured in exquisite detail, and it is enough to tell us something about how the universe worked when it was young. The final words arrive slowly, each sentence separated by a pause, each one settling into the quiet space of the studio like a soft blanket being laid over you. The universe has been making and losing stars for billions of years, the narrator says. It will continue to do so for billions more, long after our own star is burned out, long after Earth and everything on it has returned to dust. But tonight, the sky above your window is steady and familiar, the same constellations that humans have been watching and naming and telling stories about for thousands of years. One more ancient star funeral, one more supernova from the dawn of time, is simply another piece in a vast and beautiful story, a story that you are part of whether you're awake or asleep, whether you're watching telescopes or dreaming under the stars. The universe is not somewhere else, out there beyond the atmosphere and the planets and the light years of empty space. It is here. It is the ground beneath your feet and the air in your lungs and the atoms in your body, all of them forged in stars, all of them participants in this slow, unfolding process of matter, organising itself into galaxies and planets and people and thoughts. And so you can safely drift off now, knowing that the work continues, the telescopes watch, the data flows, and tomorrow or next week or next year there will be another discovery, another faint light caught after billions of years of travel, another small addition to the sum of what we know about where we came from and what the universe is like beyond the narrow slice we can see with our own eyes. The lights in the studio dim further, the backdrop of stars becomes the only illumination, and the narrator's voice fades to silence, leaving you with the image of a golden telescope in the darkness and the quiet knowledge that somewhere, always, ancient light is arriving. The silence holds for a moment, not an uncomfortable emptiness, but a spaciousness, the kind of pause that invites reflection rather than demanding it. Then the narrator's voice returns, softer now, almost a whisper, as if she is leaning in to share something more personal, more contemplative. She speaks about the nature of distance itself, how when we look at objects in deep space, we're also looking backward through time, a consequence of the finite speed of light. The photons from GRB 2503a that reached Webb's mirrors this year left their source 730 million years after the Big Bang, which means they have been travelling for more than 13 billion years, crossing a universe that was expanding all the while, stretching the space between their origin and their destination. During that immense journey, the narrator says, entire epochs of cosmic history unfolded, galaxies merged and evolved, stars formed and died in countless numbers. Our own Milky Way took shape from the slow accumulation of smaller galaxies. Our solar system condensed from a cloud of gas and dust. Earth cooled and developed oceans and an atmosphere. Life emerged and diversified and eventually produced beings capable of building telescopes and pondering their place in the cosmos. All of this happened while those photons were in transit, moving at the speed of light through the darkness, oblivious to the changes occurring around them, simply travelling in a straight line from their point of emission toward whatever might lie in their path. The visualization on the screen now shows a stylized representation of this journey. Not a literal depiction, but an artistic interpretation. A single point of light moving through a field of slowly changing shapes, galaxies appearing and growing, spirals forming, colours shifting from simpler reds and blues to more complex spectra as heavy elements become more common in the universe. The narrator explains that the universe the photons are passing through is not the same universe they left behind. The expansion of space means that distances between galaxies have grown enormously, and the wavelength of the photons themselves has been stretched, shifted from what was originally high-energy ultraviolet or visible light into the near-infrared wavelengths that Webb is designed to detect. This stretching, this redshift, is one of the most fundamental observations in cosmology, evidence for the expansion of the universe, and a tool for measuring distances to the most remote objects we can see. Without understanding redshift, the narrator notes, astronomers would have no way to determine that GRB 2503-4a came from the early universe rather than from somewhere much closer and more recent. The measurement of redshift is what transforms a faint smudge of infrared light into a window on the first billion years of cosmic history. The program lingers on the concept of measurement itself, the careful process by which astronomers extract meaning from the faint signals collected by their instruments. Webb's spectrographs split the light from the supernova's host galaxy into its component wavelengths, creating a spectrum, a graph that shows how much light is present at each particular colour. Within that spectrum there are features, narrow dips or peaks that correspond to specific elements absorbing or emitting light at characteristic wavelengths. Hydrogen has its signature pattern, as do helium and oxygen and carbon and every other element. By identifying these patterns and measuring exactly where they appear in the spectrum, astronomers can determine both the composition of the object they are observing and its redshift, how much the expansion of the universe has stretched those wavelengths from their rest values. For GRB 250314a's host galaxy, the redshift was large, indicating a distance corresponding to a time when the universe was very young, and the presence of various elements in the spectrum indicated that this was not a galaxy of truly primordial composition, but one that had already experienced some stellar evolution, some recycling of material through stars and supernovae. The narrator allows herself a brief aside about the human element in all of this, the astronomers who spend their careers developing the skills and knowledge to interpret these spectra, to distinguish signal from noise, to recognise patterns that might escape the notice of someone less trained. These are not people who make their discoveries in dramatic eureka moments, she says, but rather through painstaking analysis, checking and double-checking their measurements, running computer models to see if their interpretations make sense, collaborating with colleagues who might have different perspectives or expertise. The discovery of GRB 250314 involved researchers from multiple institutions and countries, people who specialise in gamma-ray bursts, in supernovae, in high-redshift galaxies, in spectroscopy, in theoretical modelling, all of them contributing their particular knowledge to the collective effort of understanding what this event means. Science, the narrator reminds you, is fundamentally a communal enterprise, built on the work of many individuals over many generations, each one adding a small piece to the edifice of knowledge that we call our understanding of the universe. The visualization shifts again, showing now a montage of other discoveries Webb has made since it began science operations, a reminder that the study of GRB 250314a is just one of many investigations the telescope is conducting. There are images of nearby star-forming regions, vast clouds of gas and dust lit from within by newborn stars, their colours enhanced to show different temperatures and compositions. There are portraits of distant galaxies, some of them familiar spiral or elliptical forms, others irregular and distorted by interactions with neighbours, or by the effects of looking back to times when galaxies had not yet settled into their mature structures. There are spectra from the atmospheres of exoplanets, planets orbiting other stars, revealing the presence of water vapour and methane and other molecules that might someday tell us whether life exists beyond Earth. The narrator notes that each of these investigations is addressing a different question about the universe, and yet they are all connected by the common thread of trying to understand how things came to be the way they are, how simple beginnings led to the complex present. The early supernova observed by Webb is part of this larger story, a piece of the puzzle that helps explain how the raw materials for planets and life were created and distributed through space. There is a momentary return to the concept of scale, the almost incomprehensible sizes and timescales involved in cosmic phenomena. The narrator invites you to consider that the supernova visible in Webb's images released as much energy in a few seconds as the Sun will radiate over its entire lifetime, and that this energy was released in a volume not much larger than Earth's orbit around the Sun. The temperatures and densities involved are so extreme that matter behaves in ways we can only approximate in our most powerful particle accelerators, and yet these conditions were once commonplace in the early universe, occurring every time a massive star reached the end of its life. The fact that we can observe these events from billions of light years away, that we can measure their properties and compare them to our theoretical models, is a testament to both the power of the physical laws that govern the universe and the ingenuity of the beings who have learned to decode the messages carried by light. The narrator's tone conveys not awe in the sense of fear, but rather a quiet appreciation, the feeling you might have when recognizing something both beautiful and profound without needing to shout about it. The programme now touches on the philosophical implications of such discoveries, though it does so lightly without heavy-handedness. The narrator suggests that there is something deeply satisfying about knowing that we can trace our own origins back through this chain of cosmic events, that the carbon in our cells and the oxygen we breathe and the calcium in our bones were all created in the hearts of stars and released into space by supernovae much like the one Webb observed, though of course much more recent and much closer to home. We are, in a very literal sense, made of stardust, a phrase that has become almost cliché but which remains true and profound. The discovery of an early supernova does not change this fundamental fact, but it does help us understand the timeline, the rate at which these stellar factories operated in the young universe, the mechanisms by which simple hydrogen and helium were transformed into the full periodic table of elements. Every time we learn more about the early universe, we learn more about the conditions that eventually made our existence possible, and while that knowledge does not answer questions of meaning or purpose, it does provide a kind of context, a sense of place in the vast sweep of cosmic history. The visualization now returns to Earth, showing familiar landscapes under starry skies, a desert at night with the Milky Way arching overhead, a forest clearing where fireflies drift among the trees beneath the constellations, a shoreline where waves reflect the light of a crescent moon. The narrator speaks about how the experience of looking up at the night sky has been part of human culture for as long as there have been humans, how ancient peoples navigated by the stars, marked time by their movements, wove them into myths and stories that explained the world and humanity's place in it. Those ancient stargazers had no idea that the points of light they watched were actually suns like ours, some of them thousands or even millions of light years away, and they certainly had no concept of galaxies, or the expansion of the universe, or the Big Bang. Yet in their own way, they were engaging with the same cosmos we study today, with our telescopes and spectrographs, asking the same fundamental questions about where everything came from and how it all works. The tools have changed dramatically, the narrator says, but the impulse to understand, to look up and wonder and try to make sense of what we see remains constant across cultures and centuries. The narrator mentions, almost in passing, that the James Webb Space Telescope is named after James E. Webb, the NASA administrator who played a crucial role in the Apollo program, but who is also a somewhat controversial figure, his legacy complicated by his tenure during a time when NASA discriminated against gay and lesbian employees. This is acknowledged without dwelling on it, a recognition that scientific instruments often carry the names of flawed human beings, that progress in our understanding of the universe does not erase the injustices of the past, but rather exists alongside them, part of the complex history of how knowledge is created and by whom. The telescope itself, the narrator suggests, is now its own thing, a tool used by researchers from around the world, regardless of the politics and prejudices of an earlier era, and its discoveries belong not to any one person or nation, but to humanity as a whole. The light from GRB 254A does not care about the name painted on the telescope that captured it. It simply exists, a message from the early universe waiting to be read by whoever has the means and the curiosity to do so. The closing sequence continues, each element flowing into the next without abrupt transitions, the whole broadcast designed to guide you gently from wakefulness toward rest. The narrator speaks now about the rhythm of scientific discovery, how it is not a smooth progression, but rather a series of steps, some large and some small, with periods of rapid advancement alternating with longer stretches of incremental improvement. Webb's confirmation of the earliest known supernova is one of those steps, a significant one to be sure, but not the end of the story. There will be more observations, more distant explosions detected, more data to analyse and interpret. Some future discovery will eventually surpass GRB 250314A, finding an even earlier supernova, pushing our observations deeper into the epoch of reionization, and perhaps even to the very first stars. But that future record breaker will only be possible because of the work being done now, the techniques being refined, the instruments being built, the questions being asked. Each generation of astronomers builds on the achievements of those who came before, and in doing so makes possible the achievements of those who will come after. The stars on the backdrop behind the anchor's desk seem to brighten slightly. Or perhaps it is just that the rest of the studio has grown darker, but the effect is to draw your attention to those points of light, to remind you that they are not merely decorations but representations of real objects, each one a sun, each one potentially surrounded by planets, each one with its own story of formation and evolution and eventual fate. The narrator's voice is now barely above a whisper, each word carefully chosen and deliberately paced. She tells you that it is all right to find comfort in the steadiness of the cosmos, in the fact that despite all the violence and drama of supernovae and gamma-ray bursts and colliding galaxies, the universe as a whole operates according to consistent, understandable principles. The laws of physics that governed the behaviour of the star that exploded 13 billion years ago are the same laws that govern the behaviour of matter today, and while our understanding of those laws continues to evolve and improve, the underlying reality remains constant. There is something reassuring about this, the narrator suggests, a foundation of regularity beneath all the surface turbulence, a sense that the universe is not arbitrary or capricious, but rather follows its own internal logic, accessible to patient investigation and careful thought. The next story is about to begin, please relax and enjoy. The camera glides slowly over Greenland's eastern coast, where towers of ancient ice rise hundreds of feet above dark water. Meltwater streams trace brilliant blue veins down white cliffs, and in the distance, the gentle groaning of glaciers fills the Arctic silence, a sound like the earth breathing in its sleep. The air is crisp and still, carrying the faint mineral scent of rock dust ground fine by millennia of ice movement. This is a landscape that appears frozen in time, unchanging, as permanent as stone. But beneath this frozen surface, far below the ice and the bedrock it rests upon, something warm and patient has been discovered. A hidden geography of heat that scientists have only just begun to map in detail. For years, researchers have understood that Greenland's ice sheet doesn't simply sit motionless atop the land. It flows, imperceptibly slow from a human perspective, but constantly in motion, sliding downhill grain by grain, molecule by molecule, responding to gravity and the subtle influences of temperature and pressure. What shapes this movement? What determines whether glaciers creep forward or surge toward the sea depends on far more than just the air temperature above or the ocean currents lapping at ice margins. Deep below in the mantle, that thick layer of hot, slowly churning rock that lies between Earth's thin crust and its molten core, variations in temperature create invisible patterns of heat that rise upward through miles of stone, eventually reaching the base of the ice sheet itself. In some places, this geothermal warmth melts ice from below, creating thin films of water that act as lubricant, allowing glaciers to slide more easily toward the ocean. In other places, where the mantle runs cooler, ice stays frozen firmly to bedrock, held in place by friction and cold. Until recently, scientists working to predict how quickly Greenland might lose its ice, and how much it might contribute to rising seas, had to work with rough, blurry estimates of this hidden heat. They knew it mattered. They knew that if you got the basal temperature wrong, your models of ice flow would be wrong too. But the tools to see clearly into the Earth's interior, to map temperature variations with precision across an entire region as vast as Greenland, simply didn't exist. Models of ice sheet behaviour had to make do with simplified assumptions, averages, guesses informed by limited data. It was like trying to predict how water would flow down a hill without knowing where the hill was steep or gentle, rough or smooth. Now, in the quiet laboratories where geophysicists spend their days coaxing meaning from seismic waves and satellite measurements, something has shifted. A team of researchers led by scientists at the University of Ottawa, working in collaboration with colleagues in the Netherlands and Denmark, has produced the most detailed three-dimensional temperature maps ever created of the upper mantle beneath Greenland and northeastern Canada. These maps don't show the surface, they show what lies miles below it, revealing a landscape of thermal variations, ribbons of warmer rock, patches of cooler material, all arranged in patterns that reflect the deep geological history of the North Atlantic region. The work involved combining multiple types of geophysical data, measurements of how Earth's gravity varies slightly from place to place, recordings of seismic waves from distant earthquakes as they passed beneath Greenland, and sophisticated computer models of how rocks behave under extreme heat and pressure. The computational effort alone was immense, with supercomputers running hundreds of thousands of simulations, testing different possible temperature structures until the pieces fit together into a consistent picture. What emerged from all this patient calculation was a portrait of Greenland's thermal underworld far more complex than anyone had previously documented. The mantle beneath this massive island is not uniformly warm or uniformly cool. It varies significantly from region to region, shaped by the island's long journey through geological time. The models reveal that beneath certain parts of Greenland and northeastern Canada, the mantle retains traces of ancient heat, signatures left by the Iceland hotspot, a deep, long-lived source of volcanic heat that has influenced the North Atlantic for tens of millions of years. As tectonic plates shifted and Greenland drifted slowly across Earth's surface, it passed over this hotspot track, much like a piece of paper moving over a candle flame. The heat left its mark not just in the volcanic rocks that still dot the landscape above, but in the thermal structure of the mantle itself, patterns that persist even now, warming the base of the ice sheet in specific locations. To understand how scientists can see temperatures miles beneath the surface without drilling a single hole into the Earth's interior requires understanding how seismic waves behave. When earthquakes occur anywhere on the planet, they generate waves that radiate outward in all directions, passing through the entire body of the Earth like ripples spreading across a pond. These waves travel at different speeds depending on what they pass through. In cooler, stiffer rock, seismic waves move faster. In hotter, softer material, they slow down. By recording these waves at seismic stations scattered across Greenland and analysing how their speeds vary, scientists can infer the temperature structure of the rocks the waves pass through. It's an indirect measurement, a form of planetary X-ray that requires sophisticated interpretation, but when combined with other data sources, gravity measurements that reveal how density varies below the surface, knowledge of rock physics and how minerals respond to temperature changes, it becomes possible to build detailed thermal models of the deep Earth. The new temperature maps show warm mantle material beneath portions of Greenland and northeastern Canada arranged in patterns that align with the known track of the Iceland hotspot. Tens of millions of years ago, as the Atlantic Ocean opened and Greenland separated from Europe, volcanic activity associated with the Iceland plume created massive lava plateaus in what is now Greenland's eastern coastal region. The rocks cooled, the visible volcanism ceased, but the deeper thermal signature remained, a ghost of ancient fire still radiating heat upward through the crust. This warmth doesn't create dramatic volcanic eruptions today, but it does raise the temperature at the base of the ice sheet in certain areas, sometimes by just a few degrees, enough to matter when you're trying to understand whether ice at the bed is frozen solid or wet and slippery. The path from deep mantle temperature to ice sheet behaviour involves several steps, each operating at its own timescale. Warm mantle rock beneath the crust conducts heat upward, though slowly, as rock is not a particularly good conductor. Over time, this heat raises crustal temperatures, and eventually that warmth reaches the boundary between bedrock and ice, the basal interface where the ice sheet rests on solid ground. At this interface, temperature becomes critically important. Ice at the bed of a glacier can exist in different states. If it's cold enough, it stays frozen to the rock beneath, gripping tightly through friction. But if temperatures rise to the melting point of ice under pressure, liquid water forms, a thin film, perhaps just micrometers thick in places, but enough to dramatically reduce friction. Glaciers flowing over this water-lubricated surface can move much faster than those frozen to bedrock, accelerating their journey toward the ocean, and ultimately contributing more quickly to sea level rise. The amount of geothermal heat varies across Greenland's bed, not uniformly, but in a patchy, complex pattern that reflects the underlying mantle temperature structure. In regions where the mantle runs warmer, heat flux through the crust increases, raising basal temperatures and promoting more extensive melting at the ice bed interface. In these zones, outlet glaciers, the fast-flowing rivers of ice that drain the interior ice sheet toward the coast, can slide more readily, responding more sensitively to changes in surface conditions. When summer melt increases at the surface, or when warm ocean water reaches glacier fronts, these thermally sensitive regions may speed up more dramatically than areas where the bed remains colder and ice stays locked to rock. The new mantle temperature maps allow scientists to identify these regions with greater precision than ever before, pinpointing where geothermal influence is strongest and where ice sheet models need to account for enhanced basal sliding. Beyond the direct effect on ice flow, the thermal structure of the mantle also influences how the solid Earth responds to changing ice loads. As ice, sheets grow or shrink. The land beneath them subsides or rebounds, adjusting to the changing weight pressing down from above. This process, known as glacial isostatic adjustment, depends partly on the temperature and viscosity of the mantle rock below the crust. Warmer mantle material flows more easily, allowing faster rebound rates. Cooler, stiffer mantle responds more slowly. Understanding these variations matters for interpreting GPS measurements of land uplift in Greenland, for separating ice mass changes from bedrock motion, and for refining estimates of how much ice Greenland is actually losing year by year. The new three-dimensional temperature models provide crucial input for models of glacial isostatic adjustment, helping researchers disentangle the complex interplay between ice, ocean, and solid Earth. All of this feeds into the larger question that drives so much of the research on Greenland. How quickly might this ice sheet melt, and how much will global sea level rise as a result? The Greenland ice sheet contains enough frozen water to raise global sea levels by more than 7 meters if it melted completely. A scenario that would transform coastlines worldwide, submerging cities, displacing hundreds of millions of people, redrawing the map of human civilization. No scientist expects this to happen quickly. Ice sheets respond to climate forcing over centuries and millennia, not years or decades. But even small fractions of Greenland's ice lost over the next century or two could add significant amounts to sea level rise, compounding the effects of thermal expansion of seawater and melting from other glaciers and ice sheets around the world. Current projections for sea level rise by the year 2100 span a wide range, reflecting uncertainties in future greenhouse gas emissions, climate sensitivity, and the behaviour of ice sheets. Narrowing these uncertainties has enormous practical importance for coastal planning, infrastructure investment, and climate adaptation strategies. Ice sheet models, the computational tools scientists use to project Greenland's future, require detailed input about conditions at the base of the ice. If these models use simplified or inaccurate estimates of geothermal heat flux, they may overestimate or underestimate how fast ice can flow in particular regions, leading to systematic errors in sea level projections. Earlier generation models often used coarse continent-scale averages for basal heat, or interpolated from sparse measurements that couldn't capture the fine-scale variations revealed by the new mantle temperature maps. Some models used heat flux estimates derived from regions with different geological histories, inadvertently introducing biases. The result was a persistent source of uncertainty in projections, a fuzziness in the predictions that made it harder to offer concrete guidance to policymakers and communities planning for future sea levels. With the new three-dimensional thermal models of Greenland's mantle, ice sheet modelers can now incorporate more realistic, spatially varying patterns of geothermal heat flux into their simulations. This doesn't overturn previous projections entirely, or suddenly make Greenland dramatically more or less stable than scientists thought. Rather, it refines the picture, sharpening the focus, helping to identify which regions of the ice sheet are most sensitive to basal conditions, and which outlet glaciers might respond most quickly to warming. It allows models to better capture the real heterogeneity of Greenland's bed, moving from a blurry approximation towards something closer to ground truth. Over time, as these improved models are run through multiple simulations exploring different climate scenarios, the range of possible futures should narrow and the confidence in projections should increase. It's unglamorous work, the slow accumulation of better data and better models, but it's essential for turning speculation into reliable forecasting. The integration of deep Earth structure into ice sheet modelling reflects a broader shift in Earth system science toward recognizing the interconnectedness of processes operating at vastly different timescales. Climate scientists study atmospheric changes unfolding over years and decades. Glaciologists track ice flow and melt on seasonal to centennial timescales. Geophysicists examine mantle dynamics and tectonic processes that evolve over millions of years. For a long time, these communities worked somewhat separately, each focused on their own slice of the Earth system. But as the tools and data have improved, it has become increasingly clear that these processes don't operate in isolation. The solid Earth influences climate and ice sheets. Ice sheets and oceans load and reshape the solid Earth. Atmospheric changes force glaciers. Glacier meltwater feeds back into ocean circulation. Understanding the full system requires bringing these perspectives together, building models that span from the deep mantle to the atmosphere, from ancient geological history to near-future climate projections. Recent advances in technology have made this integration more feasible. Machine learning techniques are being applied to map subglacial topography, the hidden landscape of valleys, ridges and basins beneath the ice, using sparse radar measurements and physical constraints to fill in gaps and create high-resolution bed maps. Satellite observations now provide near-continuous monitoring of ice sheet surface elevation, velocity and extent, generating datasets that would have been unimaginable just a few decades ago. Supercomputers allow researchers to run ensemble simulations, testing thousands of different scenarios to explore how uncertainties in one part of the system propagate through to final outcomes. Climate models are becoming more sophisticated at downscaling global projections to regional scales, capturing how temperature and precipitation patterns might change across Greenland specifically, rather than treating the entire Arctic as a uniform zone. All of these pieces, mantle temperature models, bed topography, surface climate forcing, ice dynamics, ocean heat transport, are gradually being woven together into comprehensive ice sheet models that can capture more of the real complexity. There's a strange comfort in the disparity of timescales involved in this story. Human lives unfold over decades, civilizations rise and fall over centuries, ice sheets grow and retreat over millennia, mantle temperature patterns reflect processes operating over tens of millions of years. On a day-to-day basis, Greenland's ice sheet appears unchanging. a permanent feature of the planet's geography. But zoom out to the perspective of decades, and you can see thinning along the margins, acceleration of outlet glaciers, lakes forming on the surface in summer and draining through cracks toward the bed. Zoom out further to centuries and millennia, and the ice sheet becomes a dynamic player in Earth's climate system, waxing and waning in response to orbital cycles, atmospheric composition, ocean circulation patterns. Zoom out to millions of years, and Greenland's journey over the Iceland hotspot becomes visible. Volcanic plateaus erupting and cooling, the thermal structure of the mantle gradually adjusting as heat diffuses and plates shift. The new mantle temperature maps capture a moment in this vast span of geological time. They show the current thermal state of the Earth beneath Greenland, a snapshot of deep heat patterns that have been shaped by millions of years of tectonic motion and volcanic activity. But this thermal structure is not static. It evolves, albeit slowly, as the mantle continues to convect and heat diffuses through rock. Over human timescales, these changes are negligible. The deep thermal structure will remain essentially constant for thousands of years to come. But over the longer timescales relevant to ice sheet evolution, these patterns provide a stable boundary condition, a slow-changing baseline against which the ice sheet adjusts. The mantle doesn't care about decades of human greenhouse gas emissions or century-scale policy decisions. It continues its patient work of conducting heat, convecting material, responding to loads, operating on its own deep timeline. There's something oddly reassuring in that indifference, a reminder that while human actions matter enormously for the near-term climate and ice sheet response, the Earth's deeper processes will continue regardless, following their own ancient rhythms. The immediate implications of this research are primarily for the scientific community. Glaciologists and climate modelers who can now improve their simulations, geophysicists who have better constraints on mantle structure, geologists who can refine their understanding of North Atlantic geological history. But the downstream effects reach much further. More accurate ice sheet models lead to more reliable sea level projections, which inform coastal planning, infrastructure design, insurance risk assessments, and international climate negotiations. Cities like Miami, Jakarta, Venice, and Mumbai, all vulnerable to rising seas, depend on these projections to make trillion-dollar decisions about seawalls, managed retreat, or adaptation strategies. Small island nations facing potential inundation need to know whether they have decades or centuries to plan relocations. Farmers in river deltas need to understand how saltwater intrusion might affect their fields. The global economy, still heavily concentrated along coastlines, has immense stake in getting these projections right. The path from mantle temperature maps to actionable policy is long and involves many steps, many translations between scientific disciplines and between science and society. The researchers who built the thermal models likely spend most of their time thinking about seismic wave speeds, viscosity parameters, and computational methods. The ice sheet modelers who use these models as input focus on stress balance equations, calving parameterizations, and meltwater routing. The climate scientists who provide forcing scenarios worry about greenhouse gas concentrations, radiative transfer, and feedback loops. The policy analysts and planners who ultimately use sea level projections must translate probabilistic forecasts into concrete decisions about resource allocation and risk management. Each step involves communication across disciplinary boundaries, building trust, establishing credibility, and dealing with irreducible uncertainties. The new mantle temperature maps represent one piece in this long chain, an improvement in the foundational understanding of Greenland's thermal structure that will slowly percolate through the system, eventually contributing to slightly better, slightly more reliable guidance for human societies adapting to a changing planet. Looking at the images that accompany the research, false colour cross-sections of temperature beneath Greenland, ribbons of orange and red indicating warmer mantle, blues and purples showing cooler zones, it's striking how much structure exists in what might naively seem like a uniform interior. The Earth beneath our feet is not homogeneous. It's layered, varied, full of history written in temperature gradients and compositional variations. Each colour band represents rock that has been heated, squeezed, moved, and cooled over unfathomable spans of time, accumulating a thermal memory of every major geological event that affected this region. The warmth beneath East Greenland remembers the rifting that split continents and opened the Atlantic Ocean 60 million years ago. It remembers the Iceland plume rising from deep in the mantle, punching through overlying rock to erupt as flood basalts. It remembers the slow drift of the Greenland plate across this hotspot track, the gradual cooling as distance increased, the current configuration where Greenland sits northeast of Iceland, still feeling the thermal influence but no longer directly above the hottest part of the plume. This geological memory, preserved in mantle temperatures, now becomes part of humanity's memory, encoded in databases and computational models that will inform decisions about our collective future. There's a kind of poetry in that transfer. Ancient heat patterns detected by seismometers and satellites, translated into numbers and equations, fed into supercomputers that simulate ice flow, eventually emerging as projections of sea level rise that appear in climate reports and policy briefings. The deep Earth speaks in seismic waves and gravity anomalies. Scientists listen with instruments and mathematics. Societies respond with adaptation plans and carbon emission targets. It's a slow, iterative conversation between deep time and human time, between geological processes that operate at one pace and societal processes that operate at another. As night settles over Greenland's ice sheet, the surface cools rapidly under clear Arctic skies, but the heat from below continues its steady upward march, molecules of rock passing kinetic energy to their neighbours, a diffusion process that never stops, never sleeps. Somewhere beneath the ice, at the interface between rock and frozen water, this geothermal warmth is melting ice molecules one by one, maintaining thin films of water that allow glaciers to slide, contributing incrementally to the slow discharge of ice toward the sea. The process is too slow to see, too gradual to measure in any single moment, but integrated over years and decades and centuries it matters. The ice sheet is not a static monument. It's a dynamic system in slow motion, constantly adjusting, constantly flowing, constantly exchanging mass with the ocean and atmosphere. The deep heat helps determine the pace of that adjustment, influences where the system is most sensitive to change, shapes the response to warming air and warming seas. The researchers who created the new mantle temperature maps have given their colleagues a tool, a more detailed map of one piece of the vast puzzle that is Earth's climate system. Other researchers will use this tool to build better models, run more refined simulations, publish updated projections. Those projections will be synthesized in assessment reports, discussed at conferences, debated in scientific journals, and eventually distilled into guidance for policymakers. The process will take years, the improvements will be incremental, and no single study will revolutionize understanding. But cumulatively, through the patient accumulation of better observations, better models, and better integration across disciplines, the picture of Greenland's future becomes clearer. The uncertainties narrow, the confidence increases, the projections become more reliable. It's not fast, it's not dramatic, but it's how science works, brick by careful brick, building a structure of knowledge that can support the weight of important decisions. Far beneath the ice, in darkness and heat that no human will ever directly experience, the mantle continues its slow convection, warm material rising, cool material sinking, heat conducting upward through miles of rock. The Iceland hotspot continues its deep burn, fed by processes extending perhaps all the way to the boundary between mantle and core, thousands of miles below the surface. Greenland continues its slow drift across the planet's face, a few centimetres per year, a motion imperceptible in human experience but meaningful over geological time. The ice sheet continues its own slow motion, responding to the competition between snowfall that adds mass and melting that removes it, to air temperatures that rise and fall with seasons and longer climate cycles, to ocean waters that lap at glacier fronts, to the hidden heat rising from below. All of these processes interweave, operating at their own timescales, coupled through physical laws that don't care about human priorities or concerns, but that can be understood, measured, modelled, and eventually predicted with increasing accuracy. The documentary closes as dawn begins to touch Greenland's eastern rim, golden light sliding across ice that has turned pale pink and orange in the low-angle sun. Icebergs drift in absolutely still water, their surfaces mirroring the sky, their underwater bulk hidden in dark water, carved from glaciers that have been flowing for thousands of years. Somewhere in the distance, a glacier calves, a thunderous crack and splash, blocks of ancient ice tumbling into the sea, raising waves that will ripple outward for miles. It's a small event in the life of an ice sheet, one of thousands that occur every day around Greenland's margins, but each represents a tiny contribution to the global ocean, a few molecules of fresh water joining the vast salt reservoir, an infinitesimal addition to sea level that, multiplied by countless similar events and integrated over years, becomes measurable, meaningful, consequential. The hidden heat beneath the ice doesn't cause the carving directly, but it influences the system that leads to it, warming the base of the ice stream that feeds this glacier, promoting sliding that brings ice to the coast more quickly, contributing to the delicate balance between accumulation and loss that determines whether the ice sheet grows or shrinks. Understanding that influence, mapping that hidden heat, integrating it into models. This is the work that allows scientists to project forward, to estimate how much this glacier, this sector, this entire ice sheet might contribute to sea level in the decades and centuries ahead. It's work done in laboratories far from the ice, with tools that sense vibrations and gravity, with computers that solve equations, with databases that store measurements and simulations. But it's work that connects directly to the physical reality of ice and ocean and rising seas, to questions about how human civilization will adapt to a changing climate, to decisions being made now that will affect coastal communities for generations to come. The Earth's mantle, ancient and patient, glows with heat accumulated over billions of years, heat left over from the planet's formation, and heat generated continuously by radioactive decay in minerals throughout the interior. This warmth rises slowly, powering plate tectonics, volcanism, mountain building, all the dynamic processes that shape our planet's surface. Beneath Greenland it warms rock, which warms the base of ice, which changes how glaciers flow, which influences sea level, which affects coastlines where billions of people live. The chain of causation is long but unbroken, connecting the deepest Earth to the shallowest concerns of human societies. The new thermal maps are one more link in humanity's effort to understand this chain, to predict its consequences, to prepare for what comes next. The work continues, the models improve, the projections refine, and slowly, patiently, like the ice itself, our understanding deepens. The satellite that captured the first measurements feeding into these thermal maps orbits far above Greenland, passing over the ice sheet multiple times each day, its instruments so sensitive they can detect variations in Earth's gravitational field smaller than 1 part in a billion. These tiny anomalies, places where gravity pulls slightly stronger or weaker than average, reflect differences in density deep below, places where rock is slightly denser or slightly less dense, slightly cooler or slightly warmer. The satellite doesn't see temperature directly. It sees the subtle consequences of temperature, the way heat affects rock density, the way density affects gravitational pull, the way gravity affects the satellite's orbit. From these minuscule orbital perturbations, scientists work backward through layers of physics and mathematics to infer the structure of the Earth miles below. This process of inference, of extracting signal from noise, of building pictures of invisible things from indirect measurements, represents one of the great triumphs of modern geophysics. A century ago, the Earth's interior was largely unknown territory, accessible only through speculation and the occasional volcanic eruption that brought deep material to the surface. Scientists knew the planet had layers. They could tell from its average density that something heavy must lie at the centre, and seismic waves from earthquakes revealed distinct boundaries between crust, mantle, and core. But the details, the variations within those layers, the temperature structures and compositional patterns remained hidden. Today, through the accumulated efforts of thousands of researchers, through decades of patient data collection and theoretical development, through the computational power that allows complex inversions and simulations, the Earth's interior has gradually come into focus. Not with the clarity of visible light, not with the directness of drilling or digging, but with the resolution and confidence that comes from combining multiple lines of evidence, from testing models against observations, from demanding consistency across different types of measurements. The thermal models of Greenland's mantle represent this kind of multifaceted inference. Seismic data provides constraints on wave speeds, which relate to temperature through known relationships between heat and rock stiffness. Gravity data constrains density distributions, which also relate to temperature through thermal expansion. Geological observations, the presence of ancient volcanic rocks, the structure of the crust, the history of tectonic motion, provide boundary conditions and consistency checks. Heat flow measurements at the surface, sparse though they are in Greenland, offer direct but limited sampling of the thermal state at shallow depths. Rock physics laboratories provide the fundamental relationships between temperature, pressure, mineral composition, and physical properties. All of these pieces feed into computational models that test countless possible temperature structures, searching for configurations that satisfy all the constraints simultaneously, that match seismic observations and gravity data, and geological history and physical laws all at once. The resulting models aren't perfect. No model of such a complex system can be, but they represent the best current synthesis of available evidence, and they're vastly more detailed and reliable than anything that existed even a decade ago. The improvement in resolution matters enormously for ice sheet modelling, because the behaviour of glaciers is remarkably sensitive to basal conditions, and those conditions can vary over surprisingly short distances. A glacier flowing across a landscape where geothermal heat flux varies by even 20 or 30 milliwatts per square metre from one region to another might exhibit completely different dynamics in different sectors. In warmer zones, the base melts more readily, producing water that lubricates sliding and allows rapid motion. In cooler zones nearby, ice might remain frozen to bedrock, slowing or stopping flow entirely. These differences create patterns of fast and slow ice, channeling flow into specific outlet glaciers while leaving other regions relatively stagnant. Earlier models, working with coarse heat flux estimates that averaged over hundreds of kilometres, couldn't capture this heterogeneity, and therefore couldn't accurately predict which glaciers would respond most strongly to surface warming or ocean changes. The new high-resolution thermal maps, with variations resolved at scales of tens of kilometres, allow modellers to incorporate realistic spatial patterns of basal heat, leading to more realistic simulations of ice flow patterns. This matters not just for predicting total ice loss and sea level contribution, but for understanding the mechanisms of change and identifying the most vulnerable regions. Greenland's outlet glaciers don't all behave the same way. Some respond primarily to surface melt. Warm summers produce meltwater that drains through crevasses and moulins to the bed, temporarily increasing basal water pressure and speeding up flow. Others respond more to ocean warming. Warmer Atlantic waters reaching glacier fronts increase submarine melting, removing buttressing ice and allowing upstream ice to accelerate. Still others are controlled primarily by basal conditions, whether the bed is warm enough to produce continuous meltwater, whether the substrate is hard rock or soft sediment that can deform under stress. Understanding which mechanism dominates in which glacier requires detailed knowledge of geometry, bed properties, and thermal state. The new mantle temperature maps contribute directly to this understanding, helping identify which glaciers are most likely to have warm, wet beds, and therefore which ones might be most prone to rapid change. There's also the question of how these thermal patterns might change over time, though on timescales much longer than typical human planning horizons. The heat flow from the mantle isn't entirely constant. It can vary as the mantle slowly convects and as radioactive isotopes gradually decay. The Iceland hotspot itself, though remarkably long-lived, waxes and wanes in intensity over millions of years. As Greenland continues to drift slowly away from Iceland, moving perhaps 2 centimetres per year, accumulating to significant distances over millions of years, the thermal influence of the hotspot will gradually diminish. New volcanic regions may become active elsewhere as the plate motions continue. These changes operate on timescales of millions of years, completely irrelevant to near-term sea level projections, but important for understanding the long-term evolution of Greenland's ice sheet through past glacial-interglacial cycles. During the ice ages of the Pleistocene, when Greenland's ice sheet expanded and contracted multiple times, the thermal structure of the mantle beneath remained roughly constant, providing a steady background against which the ice responded to orbital forcing and atmospheric CO2 changes. The thermal patterns visible in today's models likely influenced how ice accumulated and melted during those past cycles, helping determine which regions were most stable and which were most prone to rapid change. Looking back through ice core records drilled from Greenland's summit, scientists can read climate history directly from the ice itself. Bubbles of ancient air trapped as snow accumulated and compressed into ice provide direct samples of past atmospheres, revealing how CO2 and methane concentrations changed over hundreds of thousands of years. isotopic ratios in the ice record temperature variations marking glacial and interglacial periods, documenting abrupt climate shifts that occurred in just decades. Dust layers and volcanic ash provide chronological markers, tying the ice record to events recorded in ocean sediments and cave formations elsewhere around the globe. This archive of climate history extends back more than 100,000 years in the longest cause, providing an extraordinary window into Earth's natural climate variability before human influence became dominant. Throughout all these changes, through ice ages when global temperatures were 5 or 6 degrees Celsius colder than today, through warm periods when they were slightly warmer, Greenland retained its ice sheet, though its size and extent varied considerably. The ice core records themselves prove the sheet's persistence, but they also reveal periods of rapid change, times when ice dynamics shifted quickly in response to changing conditions. Understanding what controlled ice sheet behaviour during these past changes helps calibrate models for projecting future changes. If models can successfully reproduce the observed history, matching the timing and magnitude of past ice retreat and advance, matching the rates of change recorded in sea level indicators and ice core evidence, then confidence increases in their projections of future behaviour. But getting the models to match past behaviour requires accurate representation of all the key processes, including basal sliding controlled by geothermal heat. A model that uses the wrong basal heat flux pattern might accidentally get the right answer for the wrong reasons, or might systematically miss important aspects of ice sheet response. The new thermal maps, by providing more realistic boundary conditions, help ensure that models are reproducing past behaviour for the right physical reasons, which in turn increases confidence that their future projections are reliable. The computational challenge of modelling ice sheets continues to push the boundaries of what's possible with current supercomputers. Ice sheets are large. Greenland spans more than 1,500 kilometres from north to south, but they also have fine-scale structure that matters for their behaviour. Crevasses, moulins and ice streams create features ranging from metres to kilometres in size. Bedrock topography includes valleys and ridges at many scales. The ice itself deforms in complex ways, with viscosity that depends on temperature, stress, and crystal structure. Accurate simulation requires resolving these different scales simultaneously, running models with fine spatial resolution but over long time periods, capturing processes that operate over minutes, crevasse formation, days, meltwater drainage, years, glacier acceleration, centuries, ice thickness changes, and millennia, full glacial cycles. The computational grids required can have millions of elements, and tracking ice flow through those grids over simulated centuries requires billions of calculations, even with modern supercomputers running comprehensive ensemble simulations, testing many different scenarios with different assumptions about climate forcing, ice physics and boundary conditions, requires months of continuous computation. The researchers building these models must constantly balance resolution against computational cost, deciding which processes to represent explicitly and which to parameterize with simplified approximations. Basal sliding, for instance, is often parameterized with empirical relationships, rules of thumb that relate sliding velocity to basal stress and water pressure, because explicitly simulating the detailed fluid mechanics of water flowing at the icebed interface would be prohibitively expensive. But these parameterizations need to be based on realistic assumptions about basal conditions, which is where the improved thermal maps become crucial. A parameterization that works well for cold-bedded ice might fail completely for warm-bedded ice. Knowing which regions have which conditions allows modelers to apply appropriate physics in appropriate places. There's an interesting parallel between the patience required in computational modelling and the patience of the processes being modelled. Running an ice sheet simulation for 1,000 simulated years might require weeks of actual computer time. Processors churning through calculations day and night, storing terabytes of output data that will later be analysed for trends and patterns. The glacier being simulated moves equally slowly in its own frame of reference. A particle of ice entering the accumulation zone in the interior might take thousands of years to flow to the coast, gradually descending, compressing, warming, deforming, eventually reaching the terminus and carving into the ocean. The computation condenses this vast span of time into manageable duration, but the essence of slowness remains. Ice sheet science requires patience at every level. Patience to collect data over decades, patience to run models over weeks, patience to see how projections evolve as understanding improves, patience to wait for natural experiments like glacier accelerations to play out and provide new information. Perhaps this is part of what makes ice sheet research both frustrating and fascinating for scientists in the field. Unlike laboratory experiments that can be run in hours or days, unlike weather forecasts that verify within days, ice sheet predictions require decades to validate. A projection made today about Greenland's contribution to sea level in 2100 won't be fully testable until researchers currently in graduate school are in retirement. This creates a unique relationship between the science and its timescales. Researchers must work with the understanding that their most important predictions will outlive their careers, that the ultimate test of their models will come long after they've moved on. It requires a kind of intellectual humility, an acceptance that certainty may never arrive, that the best one can do is reduce uncertainties step by step, leaving better tools and better understanding for the next generation to refine further. The communities living around Greenland's coasts already see the changes underway. Fishermen report shifts in fish populations as ocean temperatures change. Hunters notice alterations in sea ice extent and reliability. Towns built on permafrost deal with thawing ground and destabilizing foundations. These local observations, accumulated over lifetimes and generations, provide crucial ground truth that complements the satellite data and model simulations. Indigenous knowledge systems, developed through centuries of close observation and adaptation, contain information about natural variability, about how the environment responds to different conditions, about patterns that might not be captured in the relatively short instrumental record. Integrating this traditional knowledge with modern scientific understanding represents both a challenge and an opportunity. Different ways of knowing, different epistemologies, but ultimately describing the same physical reality. For the people living in places like Ilulissat, where massive Jakobshavn Glacier carves enormous icebergs into Disco Bay, the abstract discussions of mantle temperature and basal sliding become concrete in the changing frequency and size of calving events, in the shifting positions of glacier fronts, in the increasing freshwater flux that affects local marine ecosystems. Tourism has grown around the spectacle of calving glaciers, bringing economic benefits, but also raising questions about how to develop sustainably in a rapidly changing environment. Should communities invest in permanent infrastructure when the landscape itself is transitioning? How do you plan for the future when the baseline keeps shifting? These questions don't have purely scientific answers. They involve values, risk tolerance, economic constraints, and cultural identity. But science can inform them by providing clearer pictures of possible futures, by narrowing the range of uncertainty, by identifying which changes are likely and which are merely possible. The global dimension of these local changes adds another layer of complexity. Meltwater from Greenland doesn't stay in Greenland. It flows into the ocean and redistributes around the globe through currents and tides. Sea level rise is not uniform. Earth's gravitational field, ocean currents, and land motion create regional variations, with some coastlines experiencing more rise than the global average and others less. Freshwater from melting ice affects ocean salinity and density, which influences circulation patterns including the Atlantic meridional overturning circulation, the system of currents that includes the Gulf Stream and helps moderate climate in Europe. Large volumes of fresh water entering the North Atlantic could potentially weaken this circulation, leading to complex climate, effects far from Greenland itself. These teleconnections mean that changes in Greenland's ice sheet have implications that extend well beyond simple sea level contributions, affecting climate patterns, ocean ecosystems, and atmospheric circulation across vast distances. Understanding these connections requires yet another level of modelling complexity. Coupled ice-ocean-atmosphere models that simulate all the interacting components simultaneously. The ice sheet influences the ocean by releasing fresh water and icebergs. The ocean influences the ice sheet by carrying heat to glacier fronts. The atmosphere influences both ice and ocean through temperature, precipitation, and wind. The ice and ocean influence the atmosphere through albedo effects, humidity changes, and heat exchange. These feedbacks can amplify or dampen changes, create tipping points, lead to non-linear responses where small pushes produce large outcomes. Disentangling cause and effect in such a coupled system challenges even the most sophisticated models, and observations that could validate the models remain sparse. Progress comes through careful comparison of models with observations, through process studies that isolate particular mechanisms, through natural experiments like past climate changes that test whether models can reproduce what actually happened. The mantle temperature maps fit into this larger effort as one piece of the foundation. Better boundary conditions that allow more accurate ice sheet models, which in turn can be better coupled with ocean and atmosphere models, gradually building toward comprehensive Earth system models that capture the full complexity of interactions. Each improvement is incremental. Each new data set refines understanding slightly. Each model advance narrows uncertainties a bit more. There are no eureka moments, no sudden breakthroughs that solve everything at once. Instead, there's the steady accumulation of knowledge, the patient building of infrastructure, observational networks, computational capabilities, theoretical frameworks, collaborative relationships, that enable science to slowly converge on more reliable representations of reality. Night deepens over the ice sheet, and far above, the aurora begins its dance, sheets of green and occasionally red light rippling across the sky, produced by solar particles interacting with Earth's magnetic field and atmosphere. This light show, beautiful and ethereal, represents yet another connection between processes at vastly different scales. Nuclear fusion in the Sun's core producing the energy that accelerates particles, the Earth's liquid iron outer core generating the magnetic field that channels those particles toward the poles, atmospheric atoms emitting photons as they're excited and return to ground states. The aurora has been visible from Greenland for as long as Greenland has existed, long before ice covered it, witnessed by no eyes for most of that time, a physical phenomenon, proceeding regardless of observation. The ice below, the mantle beneath that, the processes that shape them all. These two operated for millions of years without witness, without measurement, without understanding. Only in the last few centuries, and especially in the last few decades, have humans developed the tools to observe and comprehend these systems, to measure their behaviour, to project their futures. This recent acquisition of observational and predictive capability comes at a crucial moment, as human activities drive changes to Earth's climate more rapid than anything in the geological record since the asteroid impact that ended the Cretaceous period. The atmosphere's CO2 concentration has risen from pre-industrial values around 280 parts per million to over 420 parts per million today, a change that took only about 2 centuries, a geological instant. Earth's climate is responding, with global average temperatures already more than 1 degree Celsius above pre-industrial baselines and continuing to rise. Ice sheets, glaciers, sea level, ecosystems, all are adjusting to this new forcing, and the adjustments are only beginning. The full response will unfold over centuries and millennia, long after current greenhouse gas emissions have ceased, because the climate system has immense inertia. Ice sheets are particularly slow to respond, with equilibration timescales of thousands of years, meaning that even if atmospheric CO2 were stabilised tomorrow, ice would continue adjusting for millennia as it slowly catches up with the new climate state. The value of research like the new mantle thermal mapping lies partly in improving near-term projections for planning purposes, but also in understanding the longer-term committed changes already in motion. Humanity has already altered the planetary energy balance enough to ensure significant future sea level rise even with aggressive emissions reductions. The questions are how much, how fast, and over what timescales. Better ice sheet models, informed by better knowledge of basal conditions, help answer these questions, providing essential information for adaptation planning. Coastal communities need to know not just that seas will rise, but how quickly and how much, so they can make informed choices about whether to protect, accommodate, or retreat. Engineers designing infrastructure that must last 50 or 100 years need projections of local sea level over those timescales. Insurance companies assessing flood risk need probabilistic forecasts. All of these stakeholders depend on the slow, careful work of researchers, gradually improving understanding of ice dynamics, basal processes, climate forcing, and how these factors combine to determine future ice sheet behaviour. The ice itself, oblivious to human concerns, continues its slow journey, molecule by molecule, crystal by crystal, flowing downhill under its own weight, shaped by forces both visible and hidden. Above, the climate warms. Below, the mantle glows. Between these two reservoirs of heat, the ice exists in a delicate balance, maintained by the cold of polar winters and the shield of altitude, but perpetually under siege from warmth above and warmth below. For millennia, that balance held relatively steady. with the ice advancing in cold periods and retreating in warm ones, but remaining a permanent feature of the Greenland landscape. Now the balance shifts, tipping toward retreat, accelerating as feedbacks amplify the forcing. The bright white surface that once reflected sunlight back to space darkens as melt exposes bare ice and dust. Meltwater carving channels to the bed increases sliding in summer months. Ocean waters warming by fractions of a degree reach deeper into fjords, melting glacier fronts from below. Each of these effects is small individually, but together they compound, pushing the system in one direction. The next story is about to begin. Please relax and enjoy. The lava flows at night, a river of molten orange sliding down the dark Hawaiian slope with the patience of honey. Where it meets the ocean, steam rises in white plumes that glow against the starlit sky, and the rock hardens from brilliant orange to deep crimson to black in the space of seconds. Each pulse of magma emerges from the earth like a breath, slow and steady, as if the planet itself is exhaling something it has held deep inside for longer than we can imagine. Lie down now. Let your breathing match the rhythm of this flow, slow, unhurried, constant. Tonight's story is about a connection so hidden and so gradual that no human will ever witness it directly, yet it shapes the ground beneath every step we take. It's about how the metallic heart of our planet, thousands of kilometers below, is not entirely sealed away from the rocky world above. Over billions of years, material from Earth's iron core has been leaking upward through the mantle, carried in slow currents of hot rock, eventually arriving at the surface in places like Hawaii as volcanic stone. This leaking is not sudden or violent. It is gentle, exceedingly slow, part of a deep circulation that keeps Earth alive and ever-changing. Pull back now from the lava, away from the island, up through the atmosphere until Earth hangs in space before you, a sphere of blue oceans and white clouds, beautiful and serene. But imagine it sliced open like a layered cake, revealing what lies within. At the very outside is the crust, thin and brittle as eggshell, the only layer we ever touch. Below that stretches the mantle, a vast shell of rock that is solid yet flows like putty over millions of years, making up most of Earth's volume. And deeper still lies the core, an outer layer of liquid iron and nickel, churning and convecting, and at the very centre a solid sphere of metal under such immense pressure it cannot melt despite temperatures rivaling the surface of the sun. Heat escapes from this core and from the deep mantle over time, and that escaping heat drives slow convection. Imagine enormous currents of rock creeping through the mantle at speeds comparable to the growth of your fingernails. Hot rock rises, cools near the surface, then sinks again in a cycle that takes tens of millions of years to complete. The mantle is not quiet or static. It is a slow river system on a planetary scale, transporting heat and material in patterns that shape continents and ocean basins. Descend now into the mantle itself. Picture it not as empty darkness, but as a dimly glowing realm of dense rock under unimaginable pressure, lit from within by its own heat. In places, hotter rock gathers into columns and begins to rise, ascending through the surrounding mantle like a plume of warm air rising through cooler atmosphere. These are called mantle plumes, and they can persist for millions of years, feeding volcanic hotspots far from the edges of tectonic plates. Hawaii is one such place, a chain of volcanic islands built atop a plume that has been active for perhaps 40 million years or more. The motion here is almost imperceptibly slow. If you could watch the mantle in fast forward, you would see broad glowing streams rising and cooler currents sinking, everything moving with the grace of syrup poured through honey. A single loop of this convection, from deep mantle to near surface and back again, might take longer than the entire existence of humanity as a species. Think of it as the planet's deep, slow breathing. Hot rock rises like an inhale, cooler rock sinks like an exhale, over and over, in a rhythm measured not in seconds but in geological ages. Sink deeper now, down through the lower mantle, toward the very base of this rocky shell. At the boundary between mantle and core, about 2,900 kilometers below your feet, seismic waves reveal something strange. Two continent-sized regions where the rock behaves differently. These are called Large Low Shear Velocity Provinces, or LLSVPs, and they sit like vast submerged mountains beneath Africa and the Pacific Ocean. Seismic waves slow down as they pass through these regions, suggesting the rock here is denser, hotter, or chemically distinct from the surrounding mantle. Scattered around their edges are smaller, ultra-dense patches called ultra-low-velocity zones, or ULVZs, where seismic waves slow even more dramatically. These structures are enormous. Each LLSVP is wider than a continent and hundreds of kilometers tall. They are perched right at the interface between the rocky mantle and the liquid metal core, like enormous basins or mountains at the floor of a planetary ocean. Scientists think they may be leftovers from Earth's earliest days, when the entire surface was covered in a magma ocean and the interior was still sorting itself into layers. Some of that molten rock, perhaps mixed with material diffusing from the newborn core, may have sunk to the base of the mantle and solidified there, creating these strange provinces that persist today. The Pacific LLSVP sits directly beneath the ocean where Hawaii's volcanic chain grows, and some of the ULVZs nest near its edges. The hotspot above may be anchored to these deep structures, drawing its heat and material from this hidden reservoir far below. Return briefly to the surface. Imagine a geologist's hand holding a piece of dark volcanic rock from Hawaii, its surface rough and glassy, tiny crystals catching the light. In laboratories, scientists have analysed rocks like this, searching for clues about where the magma came from. In recent years, they found something surprising: subtle anomalies in the isotopes of ruthenium, a precious metal that should mostly reside in Earth's core. The chemical signature of these Hawaiian rocks doesn't quite match the average mantle. Instead, it hints that some of the material has interacted with or originated near the core itself, thousands of kilometers below. Isotopes are variants of the same element, identical in chemistry but slightly different in mass. Over time, natural processes fractionate them in characteristic ways, leaving a fingerprint that reveals an element's history. By measuring isotope ratios with extreme precision, geochemists can infer where magma's ingredients came from. The ruthenium anomaly in Hawaiian basalt suggests the lava carries with it a faint trace of the core, as if something from the metallic deep has made its way upward through the mantle and surfaced in these volcanic rocks. The connection is tenuous, indirect, but it's there, a whisper from the planet's hidden heart. Follow that whisper downward now. Imagine riding a stylized mantle plume from the Hawaiian hotspot into the depths, past the magma chamber beneath the volcano, through the brittle upper mantle where earthquakes occur, into the lower mantle where pressure turns familiar minerals into strange dense forms. The plume appears as a broad column of slightly warmer rock, glowing faintly against the darker mantle around it, rising with the patience of continents drifting. This plume likely originates near the core mantle boundary, perhaps where a ULVZ or the edge of an LLSVP focuses heat and buoyancy into an upward current. The descent is like a slow elevator ride through layers of colour and texture. Crystals deform under mounting pressure, minerals rearrange their atoms into tighter structures, temperature climbs, and the sense of weight becomes overwhelming. Not violent, but immense, the weight of an entire planet pressing inward. The plume is not a violent jet of molten rock shooting upward. It is a patient, persistent stream of slightly hotter material, making its way through the mantle over tens of millions of years, millimetre by millimetre, slower than the slowest glacier, yet unstoppable in its buoyancy. At last you arrive at the core mantle boundary, a thin, rough interface that separates two fundamentally different worlds. Above lies the mantle, solid rock that flows. Below lies the outer core, liquid metal in constant motion. Imagine it as a ragged coastline in total darkness, with ridges of dense LLSVP material rising like undersea mountains, and low-lying ULVZ ponds where partially molten rock has pooled. Just beneath this boundary, the outer core churns, a swirling ocean of liquid iron alloy, its convection generating the magnetic field that shields Earth's surface from solar radiation. Here, conditions are extreme but steady. Temperatures reach several thousand degrees Celsius, hot enough to vaporize any substance at the surface, yet the rock remains solid under pressures millions of times greater than atmospheric. The metal remains liquid, its atoms jostling and flowing in great convective rolls that twist magnetic field lines into complex patterns. This boundary is not a perfect seal. Over immense spans of time, light elements and trace metals can diffuse or leak from the core into the overlying mantle, subtly altering its chemistry and density. Picture it now in abstract. Coloured streams and glowing dots representing atoms crossing the core mantle boundary. The core and mantle are not perfectly isolated from each other. Models and geochemical evidence suggest a slow exchange of elements, silicon, oxygen, magnesium and trace metals, between the liquid iron of the core and the lowermost mantle rock. In Earth's youth, when a global magma ocean covered the surface and the interior was still molten, core material likely mixed into the base of the solidifying mantle. This early mixing prevented the planet from separating into rigid chemical layers and left a legacy of heterogeneity in the deep mantle that persists today. The leaking continues, though it is not really a leak in any dramatic sense. It is more like a drip, unimaginably slow but persistent over billions of years. Tiny contributions accumulate into noticeable differences in the chemistry of mantle regions and hotspot lavas. This deep mixing may be part of why Earth's mantle remains so active, and why the planet's evolution took a different path than more geologically stagnant worlds. Without this gradual exchange, the mantle might have stratified into chemically distinct layers that resist mixing, choking off the convection that drives plate tectonics and volcanic activity. Trace the path now from boundary to surface. Core-derived elements enter the lowermost mantle, perhaps diffusing into the dense rock of an LLSVP, or mixing into the partially molten material of a ULVZ. Over time, some of this altered rock becomes entrained in a rising mantle plume, carried upward by buoyancy. As the plume ascends and pressure decreases, parts of the rock begin to melt. These melts are less dense than the surrounding solid rock, so they separate and migrate upward, pooling in reservoirs in the upper mantle. Eventually they feed magma chambers beneath volcanoes and erupt as basaltic lava at hotspots like Hawaii or other ocean islands. Only a tiny fraction of the plume's deep chemical signature appears in each eruption, which is why sensitive isotope measurements are needed to detect it. But that fraction is enough to tell us that the material in these surface rocks has travelled from the core mantle boundary, a journey of nearly 3,000 kilometres upward through the planet's interior. The process is a kind of planetary circulation system. Old oceanic crust sinks at subduction zones, descending into the mantle where it is heated and transformed. Some of it may eventually reach the core mantle boundary, interact with the deep structures there, then resurface very slowly through plumes over millions of years. What sinks can eventually rise. What rises cools, hardens, and may one day sink again. The cycle continues, endlessly patient. Zoom out now to see the big picture. This deep recycling and mixing is not just an obscure detail of planetary science. It influences Earth's habitability in profound ways. The style of volcanism, the growth of continents, the release of gases to the atmosphere, the strength and stability of the magnetic field, all are shaped by how heat and material circulate through the deep interior. The peculiar structures at the base of the mantle, shaped in part by core-mantle interaction, may have helped keep Earth's interior dynamic enough to support long-term plate tectonics and a stable climate, both of which are essential for life. This is not about dramatic events or catastrophic upheavals, it is about slow balance. Too little internal activity, and a planet becomes geologically dead, its surface cold and unchanging, unable to recycle nutrients or regulate climate. Too much activity, and the surface might be too hostile for complex life to gain a foothold. Earth has found a middle path, a long steady rhythm where deep processes and surface environments gently co-evolve. The hidden circulation at the core mantle boundary is part of that rhythm, a quiet engine that has been running for billions of years and will continue long after we're gone. Consider the timescales involved. Imagine a time-lapse of Earth over billions of years, continents drifting across the surface like rafts on a slow current, ocean basins opening and closing, volcanic chains appearing and fading as plumes wax and wane. Core mantle exchange and plume cycles operate over tens to hundreds of millions of years. A single loop from core mantle boundary to surface and back might outlast entire species, whole mountain ranges rising and eroding away in the time it takes for one packet of deep material to complete its journey. Contrast this with human timescales, the decades of a lifetime, the centuries of recorded history. We move quickly through our days, measuring time in heartbeats and breaths, worrying about deadlines and appointments. The planet's deep machine is not hurried. It moves at a pace that makes our daily concerns seem very small and very brief, and there is something oddly comforting in that. While we focus on moments, Earth's hidden heart moves on a schedule closer to eternity, unconcerned with anything but its own slow turning. Return now to the surface, to where we began, a Hawaiian lava flow at night, viewed from a little farther away. The molten rock glows softly in the darkness, a ribbon of orange light against black stone, clouds of steam rising where it meets the sea. Above, stars appear between drifting volcanic clouds, brilliant and cold against the night. Below, unseen, the plume continues to feed magma from deep within the mantle, carrying with it faint chemical echoes of the core mantle boundary. Somewhere far beneath your feet, at a frontier you will never see, the planet's metallic heart and rocky mantle are still exchanging material in tiny amounts. This exchange, invisible and infinitesimally slow, keeps Earth's interior lively and its surface ever-changing. It is a hidden heartbeat, a warm, steady engine pulsing, quietly through geological ages, content to keep turning while continents drift, oceans rise and fall, and species come and go. Picture that heartbeat now as your own breathing slows. Deep below, at the core mantle boundary, iron atoms diffuse into rock. Somewhere in the lower mantle a plume begins its long ascent, warmer than its surroundings by just a few degrees, but buoyant enough to rise. Over millions of years, it will carry deep material upward, eventually reaching the surface as lava in some distant volcanic field. The rocks that form will carry with them a faint signature of the core, a chemical whisper from the planet's centre, testifying to a connection that spans nearly the entire radius of the Earth. This is the story of the leaking core. Not a catastrophe or a crisis, but a gentle, persistent exchange that has been happening since the planet was young and will continue for billions of years to come. It is the story of how Earth's deepest interior and its surface are not separate but connected through slow circulation. How what seems solid and unchanging is actually moving and mixing on timescales beyond imagination, and how the ground beneath us is part of a vast living system that extends from the centre of the planet to the edge of space. Let that image settle in your mind. A warm, patient engine turning far below, moving rock and metal in a rhythm older than mountains, slower than erosion, steady as the stars. The lava flows at night, and somewhere deep in the earth, the core leaks its secrets upward, one atom at a time, while we sleep and dream, and the planet continues its ancient, unhurried work. And yet there is more to understand about this quiet exchange, more layers to the story that unfold when we linger in the deep places and let the scale of planetary time wash over us. The core mantle boundary is not merely a surface where two layers meet. It is a dynamic region, a zone of interaction where the properties of matter are pushed to their limits and where the physics of our everyday world no longer applies in familiar ways. Here, the distinction between solid and liquid becomes less clear, and the very concept of a boundary begins to blur into something more gradual, more nuanced. Think about the outer core for a moment, that vast ocean of liquid metal swirling in the darkness. It is not still. Convection currents driven by heat escaping from the solid inner core create flows that can reach speeds of kilometres per year, glacially slow by the standards of water or air, but remarkably fast for the deep interior of a planet. These flows organise themselves into complex patterns, rising columns of hotter metal, sinking sheets of cooler metal, and vast rotating vortices that stretch from pole to pole. As the liquid iron moves, it carries with it magnetic field lines, stretching and twisting them in ways that sustain Earth's magnetic field through a process called the geodynamo. This magnetic field is not a minor detail. It extends far beyond the planet's surface, creating a protective bubble called the magnetosphere that deflects most of the charged particles streaming from the sun. Without it, Earth's atmosphere would be slowly stripped away by the solar wind, as happened to Mars billions of years ago. The magnetic field, generated by motion in the core, is part of what makes the surface habitable, and that motion, in turn, depends on heat flow across the core mantle boundary, which is influenced by the composition and structure of the lowermost mantle, the very region where core material may be leaking upward. The connection runs deeper still. The outer core is not pure iron. It contains lighter elements, perhaps sulfur, silicon, oxygen, carbon or hydrogen, that lower its density and melting point. Some of these light elements may have been incorporated when Earth formed, but others may continue to enter the core from the mantle, or leave the core for the mantle, through slow chemical reactions at the boundary. When iron in the outer core crystallizes onto the solid inner core, the light elements are excluded, making the surrounding liquid slightly less dense and causing it to rise. This process releases gravitational energy that helps drive the convection, adding to the thermal buoyancy from heat flow. In this way, the leaking of material across the core mantle boundary is intimately tied to the generation of Earth's magnetic field. A change in the rate of exchange, or in the composition of what is exchanged, could alter the vigour of core convection and thus the strength of the magnetic field. Over Earth's history, the magnetic field has varied in intensity and has even reversed its polarity many times, with north and south magnetic poles switching places. These reversals may be influenced by changes in the deep mantle, by the arrival or departure of subducted slabs at the core mantle boundary, or by shifts in the geometry of the LLSVPs. The deep interior and the magnetic shield that protects life at the surface are coupled in ways we're only beginning to understand. Consider also the heat itself, the energy that drives all of this motion. Earth's interior is hot for two main reasons. It retains primordial heat from the planet's violent formation, when countless collisions of smaller bodies released enormous amounts of energy, and it generates new heat through the radioactive decay of elements like uranium, thorium and potassium scattered through the mantle and crust. This heat must escape, and it does so through a combination of conduction, atoms jostling their neighbours, and convection, the bulk motion of hot material rising and cool material sinking. In the mantle, convection dominates. The rock is solid on human timescales but flows over millions of years, transporting heat far more efficiently than conduction alone could. At the core mantle boundary, heat flows from the hot core into the cooler base of the mantle. The rate of this heat flow determines how vigorously the core convects, how fast the inner core grows, and how much power is available to sustain the magnetic field. But the rate of heat flow is not uniform across the boundary. The LLSVPs, with their unusual composition and thermal properties, may act as insulators, reducing heat flow in some regions while allowing it to be more vigorous in others. This patchwork of heat flow may organise the pattern of mantle plumes, concentrating them around the edges of the LLSVPs, which is indeed where many hotspots like Hawaii are found. The presence of the LLSVPs and ULVZs also raises questions about Earth's early history. When the planet was young, only a few 100 million years after its formation, a Mars-sized body called Theia is thought to have collided with the proto-Earth in a cataclysmic impact. This giant impact melted much of both bodies, ejecting a huge amount of material into orbit that eventually coalesced into the Moon, and leaving Earth with a deep magma ocean. For millions of years, the surface may have been entirely molten, glowing red-hot under a thick atmosphere of vaporized rock. As this magma ocean slowly cooled and solidified from the top down, denser minerals crystallized and sank, while lighter minerals formed a crust that floated. But the very bottom of the mantle, in contact with the core, may have remained partially molten for much longer. Some researchers believe the LLSVPs could be remnants of this ancient magma ocean, dense piles of crystallized rock that sank to the base of the mantle and have persisted for billions of years. If so, they are among the oldest structures in the planet, silent witnesses to an era when Earth's surface was a hellish landscape of molten rock under a sky filled with vapour. Others propose that the LLSVPs could be accumulations of subducted oceanic crust, the remains of ancient seafloor that has been pushed down into the mantle at convergent plate boundaries and has settled at the core mantle boundary because it is denser than the surrounding mantle. Over billions of years, enough of this material could have accumulated to form the enormous provinces we see today. Yet another possibility is that the LLSVPs are enriched in iron or other dense elements that leaked out of the core early in Earth's history, when the core mantle boundary was hotter and more chemically active than it is now. Each of these hypotheses paints a different picture of Earth's evolution, yet all agree on one point. The deep mantle is not a simple uniform layer, but a complex archive of the planet's history, storing information about ancient processes in its structure and composition. The ULVZs, those smaller and even denser patches at the base of the mantle, add another layer of mystery. Some may be partially molten, with temperatures just above the melting point of mantle rock at those extreme pressures. Others may be rich in iron, having accumulated metal that leaked from the core or that was delivered by subducted material enriched in iron oxides. The existence of these structures challenges our understanding of how planets work. On a simpler world, one without plate tectonics or vigorous mantle convection, the interior might stratify into neat chemical layers and remain that way for billions of years. But Earth's interior is stirred by convection, mixed by plumes and slabs, and enriched or depleted by exchange with the core. The result is a mantle that is heterogeneous on all scales, from the tiny variations in mineral composition within a single rock sample to the continent-sized LLSVPs at the base of the mantle. This heterogeneity is not chaos. It is a kind of order born from complexity, a record of processes operating over vastly different timescales and length scales. A packet of rock in the deep mantle may carry with it a memory of where it came from, whether it originated as oceanic crust formed at a mid-ocean ridge, whether it spent time near the core mantle boundary absorbing heat and trace elements, whether it was melted and resolidified in a plume. Geochemists, by analysing the isotopes in volcanic rocks, can begin to read this memory, tracing the pathways that material has taken through the mantle over hundreds of millions of years. The isotopes of ruthenium found in Hawaiian lavas are one such clue. Ruthenium is a siderophile element, meaning it has a strong affinity for iron and preferentially partitions into metal rather than rock. During Earth formation, as the core separated from the mantle, most of the ruthenium should have sunk into the core along with the iron. The mantle should be depleted in ruthenium, and what little remains should have a particular isotopic composition. But some Hawaiian lavas show isotopic ratios that suggest they contain ruthenium that behave differently, that came from a source with a different history, possibly one that interacted with the core. The signal is subtle, a shift of just a few parts per million in the ratio of different ruthenium isotopes, but it is measurable and consistent across multiple samples. It suggests that the Hawaiian plume is sampling a region of the mantle that has been enriched in core-derived material, perhaps through the slow leaking of elements across the core mantle boundary over billions of years. Other isotopic systems, tungsten, osmium, helium, tell similar stories, each adding a piece to the puzzle of how the deep mantle is connected to the core and how that connection manifests in surface volcanism. Helium is particularly interesting. The mantle contains two isotopes of helium, helium-3 and helium-4. Helium-4 is produced by radioactive decay of uranium and thorium, so it accumulates over time in the mantle and crust. Helium-3, on the other hand, is primordial. It was incorporated into Earth when the planet formed and has been slowly leaking out ever since. Volcanic gases from hotspots like Hawaii and Iceland contain higher ratios of helium-3 to helium-4 than gases from mid-ocean ridges, suggesting that hotspot plumes are tapping into deep, ancient reservoirs of mantle that have retained their primordial helium. This primordial helium must have been stored somewhere in the deep mantle, isolated from the vigorous mixing of the upper mantle for billions of years. The LLS vases are candidates for such storage. If they are indeed ancient structures, they could have preserved pockets of primordial mantle composition even as the rest of the mantle was stirred and homogenized by convection. When a plume rises from the edge of an LSVP, it brings with it a sample of this ancient material, releasing helium-3 that has not seen the surface since the planet was young. The same plume also carries heat, of course, and that heat is ultimately what drives the volcanism at the surface. But the heat itself has a history. Some of it is primordial, left over from Earth's formation, and some is generated by radioactive decay. The heat from the core adds to this, flowing outward through the mantle and eventually radiating into space. The rate at which Earth is losing heat has been debated for centuries, ever since Lord Kelvin attempted to calculate the age of the Earth by modelling how long it would take for a molten sphere to cool. Kelvin's estimate, based on conduction alone, was far too short, only tens of millions of years, because he did not account for convection or radioactive heating. Modern estimates, based on measurements of heat flow at the surface and models of mantle convection, suggest Earth is losing about 47 terawatts of heat, roughly the energy of 10,000 large power plants running continuously. Of this heat, Perhaps 5 to 15 terawatts comes from the core, with the rest generated in the mantle and crust by radioactive decay. The core, despite being enormously hot, is gradually cooling as it loses heat to the mantle. This cooling causes the inner core to grow as iron crystallizes from the liquid outer core, releasing latent heat and light elements that drive further convection. The process is self-sustaining as long as there is heat to lose, and models suggest it will continue for billions of years, until the core has cooled to the point where convection ceases and the magnetic field dies. But the rate of core cooling depends on the thermal conductivity of the lowermost mantle, and this is where the LLSVPs and ULVs come back into the story. If these structures act as thermal blankets, insulating the core, they slow the rate of heat loss and prolong the life of the geodynamo. If they are more conductive, or if they are eroded away by mantle convection, the core cools faster. The future habitability of Earth, millions or billions of years from now, may depend in part on the stability and properties of these deep structures, on whether they persist or dissolve as the mantle continues to churn. There is also the question of symmetry. The two, LSVPs under Africa and the Pacific, are not identical. The African LSVP is taller and more dome-shaped, while the Pacific LSVP is broader and flatter. They differ in their seismic properties, suggesting differences in composition or temperature. Why should there be two rather than one or many? And why are they located where they are, under particular regions of the surface? These questions touch on the deepest mysteries of mantle dynamics. One possibility is that the locations of the LLSVPs are controlled by the pattern of subduction at the surface. Slabs of oceanic crust sink into the mantle at subduction zones, and over time these slabs may accumulate in certain regions of the deep mantle, building up piles of dense material. Computer models show that subduction patterns can organize themselves into long-lived configurations, with slabs preferentially sinking in some regions and avoiding others. The regions where slabs accumulate could become the LLSVPs, while the regions they avoid could become pathways for plumes to rise. This would create a kind of planetary-scale circulation pattern. Slabs sink at convergent boundaries, descend through the mantle and pile up at the core mantle boundary in preferred locations. The piles act as anchors, around which the rest of the mantle flows. Plumes rise from the edges or tops of the piles, fed by heat from the core and carrying with them material that has been enriched by interaction with the core or with the subducted slabs. The plumes reach the surface at hotspots, feeding volcanoes that create island chains and flood basalts. Eventually, the volcanic rocks at these hotspots are carried away by plate tectonics, subducted, and sent back down into the mantle, completing the cycle. This cycle operates over hundreds of millions of years, but it is not a closed loop. Material is constantly exchanged between different reservoirs. The crust, the depleted upper mantle, the enriched deep mantle, transition zone, the LLSVPs, and the core. Some material may circulate rapidly, returning to the surface within a few 100 million years. Other material may become trapped in the deep mantle, isolated from the surface for billions of years, and a small fraction may exchange with the core, carrying trace elements back and forth across the core mantle boundary over the entire age of the Earth. The result is a mantle that is neither well mixed nor perfectly layered, but something in between, a marble cake of compositions, temperatures and histories, stirred but not homogenized, retaining memory of the past while constantly evolving. This is the mantle that feeds the volcanoes we see at the surface, and it is why volcanic rocks are so diverse in their chemistry and isotopic composition. Each volcano is sampling a different part of this heterogeneous mantle, and by studying the rocks carefully, we can begin to map the mantle's internal structure and trace the pathways of material circulation. The implications extend beyond geology. The gases released by volcanoes, water vapour, carbon dioxide, sulfur dioxide, and many others, have shaped Earth's atmosphere and climate over billions of years. The early atmosphere was likely dominated by gases outgassed from the interior, with oxygen only becoming abundant after photosynthetic life evolved and began producing it as a waste product. Even today, volcanic outgassing plays a role in the carbon cycle, releasing carbon dioxide that would otherwise be locked away in subducted carbonate rocks. Over millions of years, the balance between volcanic outgassing and the removal of carbon dioxide by weathering and subduction helps regulate Earth's climate, keeping it within a range that allows liquid water to exist at the surface. This regulation is not perfect. Earth has experienced ice ages and hothouse periods, but it has been remarkably stable compared to other planets. Venus, with a thick carbon dioxide atmosphere and surface temperatures hot enough to melt lead, may have lost its oceans early in its history due to a runaway greenhouse effect. Mars, with a thin atmosphere and a cold, dry surface, may have lost much of its atmosphere to space after its magnetic field shut down. Earth, by contrast, has maintained liquid water at its surface for at least 3.5 billion years, perhaps longer, allowing life to originate and evolve into the complex biosphere we see today. The deep circulation of the mantle, the exchange of material with the core, the generation of the magnetic field, the release of gases through volcanism, all of these processes are interconnected, forming a planetary system that has sustained habitability over immense spans of time. And at the heart of this system, literally, is the core mantle boundary, where heat and material flow between the metallic heart of the planet and the rocky shell that surrounds it. Imagine returning once more to that boundary, to the ragged interface in the deep darkness. Iron atoms vibrating with thermal energy occasionally break free from the liquid metal of the outer core and diffuse into the overlying rock. Silicon or oxygen atoms from the mantle dissolve into the liquid core. The exchange is reciprocal, driven by differences in chemical potential and temperature, governed by the laws of thermodynamics operating at conditions we can only approximate in laboratories. Over billions of years, the cumulative effect of this exchange is to blur the distinction between core and mantle, to create a transition zone enriched in both rock-forming and metal-forming elements, a hybrid region that belongs fully to neither realm. This transition zone may be where the ULVs reside, patches of rock that are unusually rich in iron or partially molten due to the presence of core-derived elements that lower the melting point. Seismic waves struggle to pass through these zones, slowing down and scattering in ways that reveal their presence but leave their detailed structure uncertain. They are thin, perhaps only a few tens of kilometers thick, but they are dense enough to affect the dynamics of the core mantle boundary, perhaps influencing where plumes nucleate or where heat flow is concentrated. Plumes rising from the boundary may entrain some of this material, carrying it upward as they ascend through the mantle. The journey is long and the conditions change dramatically along the way. Pressure drops by more than 1 million atmospheres, temperature decreases by over 1,000 degrees, and minerals transform from one crystal structure to another as they pass through different stability fields. The plume material partially melts as it rises, with the melt fraction increasing as pressure drops and volatile elements like water or carbon dioxide. If present, lower the melting temperature further. By the time the plume reaches the base of the lithosphere, the rigid outer shell of the Earth, it has been transformed. What began as solid rock at the core mantle boundary is now a mixture of solid crystals and liquid melt, with the melt enriched in elements that preferentially enter the liquid phase. This melt is buoyant, less dense than the surrounding solid rock, so it segregates and rises, percolating through the matrix of crystals like water rising through a sponge. It collects in magma chambers beneath volcanoes, where it may reside for thousands or millions of years, slowly crystallizing and evolving in composition before finally erupting at the surface. The eruption itself is a release, a sudden opening of a pathway from the deep interior to the surface. Magma rises through fractures in the crust, driven by the pressure of dissolved gases expanding as pressure decreases. At the surface, lava pours out, glowing and incandescent, cooling in the air or ocean water. Gases bubble out, forming clouds of steam and volcanic fumes, and the rock, once it solidifies, becomes part of the crust, a new addition to the skin of the planet, but carrying within it a chemical memory of its long journey from the deep mantle, perhaps from the very edge of the core. This is how the core's secrets reach the surface, not directly, but through a long chain of processes, each transforming the material a little more, each adding its own signature. The geochemist, examining a hand sample of basalt, is reading a message written in isotopes and trace elements, a message that has travelled 3,000 kilometres and taken millions of years to arrive. The message is faint and fragmented, but it is there, testifying to the connectedness of the planet, to the way that the deepest interior and the thinnest surface layer are linked by the slow circulation of the mantle, and so the cycle continues, as it has for over 4 billion years and as it will for billions more. Slabs sink, plumes rise, The core cools and the mantle flows. Material moves between reservoirs, mixing and separating, enriched and depleted, carrying heat and elements and isotopes from one region to another. The surface is constantly renewed, old crust recycled into the interior and new crust generated by melting. The magnetic field flickers and reverses but persists, shielding the surface from the solar wind. The climate fluctuates but remains within bounds that allow liquid water and life. None of this happens quickly. A single human lifetime is far too short to observe the motion of the mantle or the drift of continents. But our species has existed long enough and developed the tools to see far enough that we can begin to perceive these slow processes, to measure their rates and trace their effects. We can send seismic waves through the planet and map its internal structure. We can measure isotopes with enough precision to detect the fingerprint of the core in a volcanic rock. We can build computer models of mantle convection and test them against observations. And piece by piece, we are assembling a picture of how the planet works, how its many parts interact, and how the system as a whole has sustained itself over deep time. The story of the leaking core is part of that larger picture. It tells us that the boundaries we draw on diagrams between crust and mantle, between mantle and core, are not absolute barriers but permeable interfaces across which material and energy flow. It tells us that the planet is not a static structure but a dynamic system, constantly evolving, its past inscribed in its present structure, its future shaped by processes that began billions of years ago and will continue long after our time. There is a deep comfort in understanding this, in seeing ourselves as brief witnesses to a system so much older and larger than we are. The lava flows in Hawaii tonight, as it has flowed for millions of years and as it will continue to flow for millions more. The plume beneath the islands rises, fed by heat from the core mantle boundary, bringing with it traces of the planet's metallic heart. And deep below, in the total darkness, iron atoms continue their slow diffusion into rock, patient and persistent, contributing their tiny part to the grand circulation that keeps the planet alive. Let your mind rest on that image, the warm darkness of the deep interior, the slow upwelling of heat, the patient exchange of atoms across a boundary far below, and the eventual emergence of that deep material at the surface as glowing lava under the stars. It is all connected, all part of one vast planetary system, operating on timescales that dwarf our own, but proceeding with a regularity and persistence that is, in its way, deeply reassuring. The Earth abides, its hidden heart beating quietly through the ages, and we are here, for this brief moment, to marvel at its workings and to tell its story.